Hey, I just wanted to quickly plug that if you guys want any tutoring, some new slots have opened. If you look in the description, there's a link to my physics and maths tutor profile in which I do tutoring on there. Alright, so welcome back to another episode of the A-Level Cookbook. Today we're going to be doing the OCR A-Level Chemistry A, June 2022 paper, paper 1. So it says an aqueous solution contains a mixture of chloride, bromide, and iodide ions. So AgNO3 is added to this mixture, followed by an excess of dilute NH3, and the resulting mixture is then filtered. Which compounds are present on the residue of the filter paper? So when you're adding silver nitrate to all of these, you're going to make precipitates, which then dissolve depending on how much dilute or concentrated ammonia you add. So for the Cl minus, Br minus, and I minus, you get a white precipitate, a cream precipitate, and then a yellow precipitate. This will dissolve in dilute ammonia. This will dissolve in concentrated ammonia. This will not dissolve in ammonia. So then, if they've added excess of dilute ammonia, it means this will have dissolved, the other two will not. So in that case, it's got to be AgBr because the Br minus, and then AgI, so it's D. Next, 20 centimeters cubed of nitrogen gas reacts with 10 centimeters cubed of oxygen to form a 20 centimeters cubed of a gaseous product. So just as a quick reminder, PV equals nRT, right? So if I just rearrange this to moles, it'd be PV over RT equals N. Now, provided that the pressure and the temperature and R are the same, then N is essentially proportional to the volume. And you can assume that in these kinds of questions. So if N is proportional to its volume, it means that if I have, for example, like, I don't know, 1 mole gives me, for some reason, 10 centimeters cubed of this, then 2 moles of that should give me 20 centimeters cubed of this. So in that case, if they've told you that you have 20 centimeters cubed of nitrogen gas plus some amount of oxygen gas, and it gives you this mysterious product, but there's 20 centimeters cubed of that, that's going to be a half O2 if that's 20 to 10, and then 20 there. So whatever this product is going to have 1, and so forth. So in this sense, if we have a look, it's any option that fits that ratio. So if we look at A, that's a 1 to 1 to 2. Well, that wouldn't make sense because that would be, what, 10, 10, 20. In B, it's a 1 to 2 to 1. So that would be, what, 10, 21. So no. If you look at C, it would be 2, 1, 2. 2, half 1. Sorry, 1, half 1. 2. If you times that whole thing by 2, that's 2, 1, 2. So it's C. If you look at D, that's 2, 2, 4. That would be what? That would be like what? If we said that was the 20, then that would also be 20, then that'd be 40, so that doesn't add up. So again, if PV equals nRT, these formulas have to work if these assumptions are made, otherwise they can't. So as long as your pressure R and temperature are the same, which you can in these kinds of questions, then the volume is proportional to the moles. Okay, so 0.541 grams is reacted with oxygen to give you that, and that's the amount of oxygen added. So the oxygen added must be the difference between those two. So 0.790 minus 0.541. If we do that, 0.790 minus 0.541, it gives you 0.249, right? Fine. If we work out the moles of the O2 added, because we're adding O2 each time, it'd be 0.249 divided by the moles of the oxygen, which would be, the MR of oxygen would be 16 times 2. So if we do that, we would get 7.781 times 10 to the minus 3, right? So store that number somewhere. Now, if we do a quick sketch of this reaction, it's going to be x plus some amount of O2 makes x2O3, right? So that's going to be 2x there, and that's going to be 3 there, so 3 over 2. So that means the molar ratio of 2 to this is 3 over 2. So what I can do is I can divide 7.781 times 10 to the minus 3, divide it by 3 over 2. That'll turn it back into just a visit 1, and then I'll times that by 2. So if I do that, divided by 3 over 2, and then if I times that by 2, it'll give us the moles of this 2x, which is 0.010375. So we now know that the moles of the 2x is going to be 0.010375. Cool. So if we know that moles equals mass over mR, or in this, mR. Now the mR of this thing here is x. It's not the 2x, it's just x. If it was x2, then it'd be 2x, but it's just x there. That 2 is the whole thing times up. So if we have the mass over mR, we know that mR equals mass over moles. So it's going to be the mass of this thing, which we've worked out 0.541, they've told us in the question, over the moles. So that's going to be 0.010375. If we do that, then we get 52.1. And if we look at our periodic table, the thing that has a mass closest to that is chromium, so it's B. Hydrogen peroxide, H2O2, can be oxidized by manganate ions under acidic conditions as shown. 2MnO4 minus plus 5H2O2 plus 6H plus gives you 2Mn2 plus 5O2 and 8H2O. Fine. In a titration, 25 centimeters cubed of a disinfectant that contains hydrogen peroxide reacts with 22 centimeters cubed of this stuff here. What is the concentration of H2O2 in the disinfectant? Assume that only this KMnO4 reacts with the H2O2 in this disinfectant. So, what they're doing is they've got this disinfectant and they're adding the KMnO4 in it. Now, the K part is irrelevant. This is just a salt that will dissolve into K plus and MnO4 minus. The reason that we do KMnO4 instead of just MnO4 minus in these equations is because in these questions is because it's just a way of putting the MnO4 minus in. So, for example, you might see questions where it's got OH minus in it, and then it says like a student puts sodium hydroxide in. That's just because you can't have OH minuses just chilling on their own. That's it. So here it says assume that only the KMnO4 reacts with this H2O2. So that means that this volume and this concentration of KMnO4 has reacted with the hydrogen peroxide in there. So that means the moles of the MnO4 minus is going to equal, because that's the thing that's reacting here. It's going to be 0.125 times 22 over 1,000. If we do that, so 0.125 times 22 over 1,000, we get 2.75 times 10 to the minus 3 moles. Now, the general tip in chemistry is that you really need to understand, not just working out moles randomly, but like what's reacting with what specifically. So before this reaction, nothing had reacted, and then they added this, and this was the only thing reacting with, and they've told you, hydrogen peroxide. So that means, on that basis, that that is reacting with that, as in those two are relevant. So that means that the moles of H2O2 equals that answer divided by 2 times by 5. The reason I say that is because I see a lot of people sort of blindly work out moles and then try and mix and match numbers and hope they're getting somewhere. It's like, if you general advice, and force yourself to do this when you're practicing, is when you're working out the moles, think, why am I doing this? Or just anything, to be honest, calculations-wise. Why am I doing this? And what am I going to do directly next with it? If you can answer both of those questions, you know what you're doing. If you can't, then you don't know what you're doing, and you should probably get that looked at. So if you do that, we've now got the moles of the H2O2, so then you know that the concentration is going to be the moles over its volume, which is that answer, divided by the volume, which is 25 times 10 to the minus 3, or 25 over 1,000, whichever way you fancy. And if we do that, that gives us 0.275, which is C. Next. So now it says the mass of 4 molecules of this substance is 2.125 times 10 to the minus 22, right? So what's the possible formula of that? So all of the masses in a periodic table, they are all the Avogadro's number of that molecule. So for example, if you look at carbon, its mass is 12, and the masses in the periodic table are all in grams per mole, meaning 1 mole of this weighs that many grams. So if I look at sodium, that's 23 as its mass. That means 23 grams is how much it weighs if I had 1 whole mole of those, which is an Avogadro's constant, which is 6.02 times 10 to the 23. So if we're going to work out the formulas, we're going to have to figure out the mass of this thing in grams per mole. We only have 4 molecules here. So that means 1 molecule is going to equal the 2.125 times 10 to the minus 22 divided by 4. So if I do that, 2.125 times 10 to the minus 22 divided by 4, that will give us like 5.3125 times 10 to the minus 23. That's 1 molecule. But remember, the periodic tables are all in grams per mole. So that's a grams per molecule. 1 mole is going to be that 6.02 times 10 to the 23 molecules. So in that case, we're going to times that by Avogadro's number. So 1 mole of it is going to be your answer times Avogadro's number. So if we do that, it gets 6.02 times 10 to the 23. It gives you 0.98 something. So now we have to just go through all of these and figure out what mass would probably fit that. So if we do that, CH4 is 12 plus 4, that's 16. Nah. O2 is what, 16 plus 16, so that's 31.98, 32, it's B. There you go. Prussian blue, C18, Fe7, N18 is a deep blue pigment that contains Fe2+, Fe3+, and Cn- ions. What are the numbers of Fe2+ and Fe3+ ions in one formula unit of C18, Fe17, and 18? So in this example, it's not charged overall. So that means we have some number of 2 pluses and 3 pluses that are going to make it neutral overall. So we know we have N18. It's safe to assume that that's going to be 18 Cn minuses. So that gives you a minus 18. So some number of Fe2 pluses and 3 pluses will give you that. And the thing is we have 7 Fe2 pluses or 3 pluses. So we need to think of a way to divvy them up, basically. So if we look at the options, let's see what happens. So if we can try and rule any out. So they're all 7s. Unfortunately, that's not an easy way of doing it. But if we look at the charges, now we know that we have to make them become minus 18 to become an overall charge of nothing. So that's 2 times 2 is 4. So 4 plus 15, that's 19. because 3 times, so that's, yeah, that one's out. And then if we look at the next one, that's 3 times 2 is 6, and then 4 times 3 is 12, 18, so that adds up, so it's B. There you go. Next. Bond enthalpies are shown in this table. What is the enthalpy change in kilojoules per mole for this reaction below? I absolutely hate the bonds before, bonds after, or bonds broken, bonds made BS. This is easy if you just do a Hess's law cycle. It literally is like an absolute game changer and you'll always get it right. When you learn Hess's law cycles, I'm going to make a video on this because no one can do it right. It actually really annoys me, okay, is you need to know the definitions and you're sorted. So if we look at bond enthalpy, the bond enthalpy is the average enthalpy change when 1 mole of a bond, blah, 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 whatever, right? The way I think of it is you're breaking 1 mole of bonds into like just eventually elements and stuff like that, right? So what I would do in my cycle is I would rewrite the equation HCH4 plus 2O2 goes to CO2 plus 2H2O. How to decide what goes on the bottom is you look at the enthalpy change that you've been given and see what you've been given in the question in the table. So this says 1 mole of bonds to elements. These are all those bonds, 1 mole of bonds, right? So those aren't the elements, and these are all of those bonded things combined, all those moles of bonds together. So I know at the bottom, elements has to go there, because these are going to be bond enthalpied into elements. So if I do that, that means the arrows all have to go down. And then you can just quickly sketch the rest out, because the CH4 there, so you're going to have 4 lots of the CH bond, which is 4 lots of 435. We know we've got 2 times the O2 bond, so that's what, here we go, 2 lots of 498. And then we know we have CO2. CO2 is this. So that means we've got 2 COs. So that's going to be, where is that? Where are you? 2 times 805. And then we know H2O is this. And we've got 2 of them, so it's going to be 4 lots of the H2O bond, which is 4 lots of 464. So if you look at what's in the table that they've given you, and any enthalpy question in the universe, even Born-Haber cycles as well, you can easily churn out a cycle like this. Because if you start and finish at the same points, Hess's law says the reaction enthalpy change is the same as long as you start and finish at the same point, no matter what route you take. So I can Hess's law this, and it saves me from having to remember 2,000 different methods and getting it wrong and then be like, oh my god, I can't do it. Just make a cycle every time. Anytime you got something where it's like, find the enthalpy change of this using other enthalpies, cycle it every time. Because then that's the enthalpy change you want. That's just going to equal, so it's going to be 4 lots of 435 plus 2 lots of 498. And then because after this we're going against the arrows, it's going to be minus 2 lots of 805 minus 4 lots of 464. And that gives you minus 730, which is A. There you go. And you'll never get it wrong if you can hack doing that. And it also forces you to learn them definitions and actually understand it. If you're having to complain about learning the enthalpy change definitions, you don't know what you're doing, and the topic you're fumbling entirely, is my personal opinion. I actually think the enthalpy change topic is probably one of the more reasonable topics in the entirety of chemistry. So if you're complaining about learning definitions, you're not using them right. Next, it says the half-life for a first-order reaction is this. What is the rate constant K in this? So the half-life is the time taken for half of the reactant to be used up. Now, what happens is in first-order reactions, you have, if something halves, it'll half and half and half and half and half. And it's told you it's first order. So what that means is at 80 seconds, you will drop by a half. So if we look at a first-order reaction, you can work out the rate constant using the half-life. Because if we use the exponential relationship, because again, it's as you're dropping, as you're dropping the concentration, that's also dropping, so it's an exponential thing. You would have K equals ln2 over the time for the half. You can remember that and memorize it. So if that's the case, then we're looking for K, and it's going to be ln2 over that half. So it's going to be K equals ln2 over 80, which is going to equal 8.864 times 10 to the minus 3. Which is going to be A. I could delve into the maths of this, but for the sake of time, I won't. But you can just remember that in first order reactions, you can do that. Now it says, what is the enthalpy change of the atomization of bromine? So the enthalpy change of atomization of bromine is where you are making 1 mole of gaseous atoms from an element in its standard states. So that's why I say the definitions are really important, because it's 1 mole gaseous atoms from an element chilling. So if we're going to do that, it's got to be whatever makes 1 mole of gaseous atoms. So that's out and that's out. So our options are Br and Br here. So if we look here, that's half Br2 liquid to half Br2 gas. Bromine exists naturally as a liquid in its own standard state, so it's A. It's not that, because that starts as a gas. Bromine doesn't exist as a gas in standard conditions. So that's why those definitions are really important, because you should be able to sort of arrow them out, being like, we start with this and you finish with this. Next, it says, for the condensation of ammonia gas, what are the signs of delta H and delta S? So think about what's going on. So we've got a gas and we're condensing it. So that means we're going to go to a liquid. If we're doing that, the gas is more disordered and more all over the place and random than liquid. So that means we're decreasing in our entropy. So delta S is negative. So those two are out. Now we have delta H is negative and delta H is negative and delta H is positive, delta H is negative. So we need to think about what's happening in terms of bonds, right? So if you're going from gas to liquid, more bonds are being made. If you're making bonds, energy is released. It's exothermic, so that means energy going out. So delta H has to be negative. So it's got to be A. Breaking bonds is positive. So if I was going gas to liquid, I'd be breaking the bonds between the ammonia, so the hydrogen bonds between all of them, and that means I have to put energy in. That's why it's endothermic. So that would make delta H positive. And if we're going from gas to liquid, liquid to gas, it's becoming more disordered, so delta H would be positive. So that one's out as well. But that's why it's A. Next, it says the equilibrium equation for an indicator HA is shown below. The indicator is added to a solution and it turns yellow. An excess of aqueous sodium hydroxide is then added. Which statement describes how the color of the solution would be expected to change? So in these, HA is an acid, A minus is a base, and then H plus is just H plus, right? Anything in the universe that can put out an H plus is an acid, because an acid is a proton donor. To donate a proton means putting that out. Anything that can react with an H plus or accept it is a base. So that means it's a base. So for example, if I have HCl, an H plus and Cl minus, that is an acid because it can go off to give an H plus out. This is the base, the conjugate base, because that can react with an H plus to give you this. So it's important to really make sure you understand that distinction of acid-base equilibria stuff and really think of it in the definitions. The definitions of proton donor and acceptor have to work, otherwise every single thing in chemistry doesn't in that sense, and it'd have to be redone. So if we look at NH3 as well, NH3 plus AH plus can make NH4 plus. So the acid is whatever puts out an H plus. So that's your acid, because there's an H plus being given out as a result. It's missing the H. It can go on to miss the H plus. The base is whatever can accept a proton and react with it. So that's the base. It's really important you understand that concept, because I get a lot of people say, "Oh, an acid is a proton donor," and then absolutely can't tell me anything about what it means in a chemical equation. In this reaction, we've added an indicator and it turns yellow. So it means we've got some A minus going on. An excess of aqueous sodium hydroxide is then added. So if you're adding excess sodium hydroxide, you're adding OH minus. So you need to look at this and think, what's the OH minus going to do? If we added H plus, then that means that would go up and the equilibrium shift that way, blah, blah, blah. But we don't have OH minus in this equilibrium. So we're not going concentration higher or lower, right? But then this OH minus will always react with an H plus because it's a proton, it's a base. It wants that proton acceptor. So what it will do is it will react with that and it will form H2O. These are how buffers also work, the acidic buffers. So if it reacts with that to make H2O, that means your concentration of H plus is going to go down. The Chatelier's principle says that an equilibrium will shift to counteract the change that is made to an equilibrium. We've just made a change. We've just decreased H plus. The equilibrium is going to shift to the right, meaning we're going to make more H plus and also more A minus. So it actually starts to go more yellow. Or stays yellow. So it would be D. It wouldn't be blue, it wouldn't be blue because it means it's shifting that way. And the only way it would do that is if we had too much of either of these. So that one's out. It wouldn't change to green because that would be, again, shifting that way. So it'd have too much of that. And then it says color changes from yellow to green and then to blue. Well, if it went green, it means it would be this way and then this way. And again, it would only happen if we have too much of either of these. So it's not that one either. It's only D. So now it says ammonia and water react to set up an acid-base equilibrium. What are the Bronsted-Lowry acids in this mixture? So if we just have a quick look, ammonia and water. So NH3, they've told you that you're adding these two together, right? You can work on the question and just quickly work out what's going on. So they've told you those two react together. You know at least on the left it's going to be that. If it's going to make a base, then you're going to make NH4 plus, because that's the base, it's accepting a proton. That's just lost an H plus, so the other thing is the OH minus. So it's saying what's the acid? So like I just said in the previous question, if anything can give out an H plus, it is an acid, no matter what. So this NH4 plus can lose an H plus to become NH3 again, so that has to be one of the acids by definition, right? Now, this H2O loses an H plus, it gives it to that, and becomes OH minus. So that's the other acid. Anything that can accept a proton or react with an H plus is a base. So that's your base because it can be reacted with an H plus to give you this. And that's your base because it can accept or react with an H plus to give you that. So your acids are the H2O and the NH4 plus, which would be, where is it, C? Okay, cool. Next, it says standard electrode potentials for two redox systems are shown below. What is the electrode potential for Cr2 plus 2E minus gives you this? Be careful, because a lot of people jump in being like, oh, this must be oxidation, this must be reduction, or whatever. So yeah, that way around, right? But sometimes the question runs it in a different way than you would expect. For example, that's more negative, that's more positive. So if that's oxidation, that's reduction. That's what happens when you discharge a cell, as in you're letting it run normally, as in, you know, you're doing its thing and its electrons move through a circuit and so forth. If you're recharging them, then it would run the opposite way. So what's oxidized is actually reduced, and this is being oxidized. Now here, we don't know whether it's being discharged or recharged. They haven't told us, but we can tell that they've told us you're starting with Cr2 plus and you're eventually making Cr solid. So this helps us decide as well which way we're taking it, if that makes sense. So it doesn't even have to, without even knowing these two, you can figure out which way these two go. So if we're starting with Cr2 plus and going to Cr solid, we need to look at these equations and figure out which one we're starting with. So we're starting on this side with Cr2 plus, and that becomes Cr3 plus, 3 plus an E minus. Right, starting with Cr2 plus, that's dealt with that. But this doesn't have a Cr3 plus in it, so when we're combining it, this needs to disappear. So this one must be that the Cr3 plus 3E minus becomes Cr solid. And you can see that fits the overall equation we want. So if we were to combine these, you would have 3 times all of this. You'd have 3 Cr2 plus and 3 Cr3 plus gives you Cr3 plus and Cr3 plus on the other side as well. That's 3. But can you see how they're both on both sides? So they cancel out, and then you have Cr solid. So that fits the bill with what we want. And even though you don't even really have to do that, because you know you start with Cr2 plus, you're going that way and that way. So again, it's not always oxidation reduction. You have to actually think about what's going on with the question they've told you, because they might set it up differently to how you want it to be. So in that sense, if we're starting with Cr2 plus and becoming Cr3 plus, that has been oxidized. And then here, that one's been reduced. So the Cr2 plus one is actually oxidized, and this one's reduced. So again, don't fall into the trap of, oh, this must be more negative, that means it's oxidized. The question's running it differently. If that's the case, your E cell is going to equal E reduced minus E oxidized. So that means it's going to be yours minus 0.74, minus 0.42. Can you see how that's the opposite to what you're familiar with? So it's really important you read the question and double check that they're not running the circuit or the cell in a way that you're not, like, you know, in a different way to what you would expect it to be. So that would give you minus 0.32, which is A. If it was just your standard running a cell and it does its job, then it would be that would be oxidized, that one would be reduced. But they told you you're starting with this and you finish with that. So you're forcing it to run that other way. The 3 reactions below form one product only. Which reaction forms a product with non-polar molecules, right? So let's have a look what's going on. So 2CO plus O2 is probably going to make CO2, right? CO2 is linear, so it's non-polar. So there's already one in the bag. So definitely that one will. Si plus 2Cl2. What does that give us, right? SiCl4. SiCl4 is tetrahedral, so it's an Si, 4 bonding pairs, 4 bonding pairs, 4 lone pairs, right? Here. Now the way I like to think of it is almost like, imagine you've got people pulling on something and tugging it, like a pull the rope thing. If that's the rope in the middle and these are all the same electronegativity differences, the same dipoles, then overall it's non-polar because they're all pulling on this by the same degree. So that one is as well. S plus 3F2 gives you SF6, so that's 6 bonding pairs, 0 lone pairs. It's octahedral. So in that case, again, it's symmetrical, and there's the polarity of the bonds are all the same in all directions, so it's 3. So 14 is all 3 of them, so A. Next it says, which ions contain one or more unpaired electrons? So unpaired, right? So we need to go through and just quickly look at their electron configurations. So 1 second. So for this question, I've just quickly grabbed a periodic table. So up here, so I've cropped it off. That's period 1, that's period 2, that's period 3, that's period 4, period 5, and so forth. So it's really important you can quickly skim through the periodic table. This is your S block, that's your D block, that's your P block. What that means is that the outer shells of all of these are going to be S1, S2, and then this is going to be P1, P2, P3, P4, P5, P6. I've cropped off the last group by accident. And then this is your D block. So every single one of these is going to end with a D something, right? Now, periods mean the number of shells. So for example, here, that's your second period, so it's going to be 2S1. That makes sense, because 1S2, 2S1, right? That's the second period, 2S1, 2S2, 2P1, 2P2, and so forth, right? Now, when it comes to the D block, it's a bit funkier, because remember that your 4S, so remember it's 1S2, 2S2, 2P6, 3S2, 3P6, 4S2, 3D. The 4S fills first. So although these are in period 4, because the 4S is filled first, these actually end up in 3Ds, all of those first. So it's 3D1, 3D2, 3D3, 3D4, 3D5, 3D6, 3D7, 3D8, 3D9, 3D10. However, just to make things even more annoying, is that copper and chromium are a bit funky as well, as they don't follow that pattern. But generally speaking, you can quickly jump through them like that, if you remember that copper and chromium are the weird ones. So if we look at Mn, right, that's D1, 2, 3, 4, 5. So we know that it's in period 4, but remember the 4S fills first, so it's going to be 4S2, 3D5, right? Now it's told you that we've lost 3 electrons, that's going to be, the 4s gets lost first, remember, so that's going to be 4s0, 3d1, right? And it's telling you that's one or more unpaired electrons, so 15, well, one of them definitely has to be you. Next, vanadium, so it's d1, d2, d3, so it's going to be 4s2, 3d3. If we have 3 plus, that means we're going to lose, so it's going to be 4s0, 3d2. That's 4s0, 3d2. But remember that electrons fill orbitals in a subshell singly before they start sharing. So in this d orbital, there's 5 of those, and there's 2, they're filled up singly. So that's definitely another one. Now, copper's a weird one, because that's what, d1, d2, d3, d4, d5, d6, d7, d8, d9, right? You'd think that'd be d9, which would be 4s2, 3d9. But it prefers to be more stable by having 4s1, 3d10 instead. And chromium's the other weird one, because that'd be d1, d2, d3, d4. So it would be 4s2, 3d4. But again, one of those electrons goes up there, 4s1, 3d5 instead. And that makes it more stable. So if we're looking at, so back to the copper, it's actually 4s1, 3d10. If it's Cu+, that's 4s0, 3d10, and that's full, so it's not that one. So it's only 1 and 2, which is B. So now it says a catalytic converter in a car removes nitrogen monoxide, NO, and carbon dioxide, CO, from the exhaust gases. One of the reactions that take place in a catalytic converter is shown below, so there's that. And then it's explain how increasing the temperature increases the rate using a Boltzmann distribution. Sketch it and label the axes. So on this axis, it's always your number of molecules or particles or whatever you want to call it, and then here is your energy. So it's telling you to draw a sketch on how increasing the temperature will do this. So generally speaking, in a Boltzmann distribution, you'll have some amount of particles having this much, and then as it goes down, it starts to level off, but it never really hits 0. It's really hard to draw on this whiteboard, sorry about that. Okay, that's for a given thing. And let's say your activation energy is kind of like there. So if you're above this, these molecules above that have enough energy to react. Let's call that like just the, I don't know, the original temperature, TO, right? Now, if I want to increase the temperature, what will happen is more particles will have a higher amount of kinetic energy, but we only have the same amount of molecules. So you can't just do this, because that means you're adding just way more particles into the system. What happens is that curve has to shift this way like that, because then you're increasing the energy of these particles, because on average, you can see the whole curve sort of shifted that way, and it slumps down because you can't add extra particles in, because there's non-extra ones. If you did the area under the graph, that's the total number of particles and their energy. That's the total energy in the system and the particles. If we added more particles, then it would do that. But we aren't adding more particles. We're only changing the temperature. So it skews the graph like this, and it actually stays lower like that. If I can try and draw it right, like this. But it's stretched towards the right, like that. So here it's saying explain how increasing the temperature increases the rate. So look at the question and just think directly what's going on. So every time you're doing a question, establish the facts of the question. So look at the text of the question and think what's happening to lead to what. Any explain or suggest one. They've told you increasing temperature means increasing rate. So that's all you have to talk about. You need to think in your head, why does that do that? And then you go, oh well, it means that, higher temperature means more particles have more kinetic energy, and then they'll have enough activation energy, the minimum, all that stuff, to collide and react. And also the increased temperature means more kinetic energy. More kinetic energy, so there's more collision. Actually, while we're on this topic, any reaction in the world requires 2 bare bones things. 1, they need to collide, otherwise they're not going to react. But 2, they can also collide and still not react. They need to have the activation energy. If you've met those 2 things, then, your reaction will happen. Now, if we try and up any of these, then the rate goes up. That's why we use catalysts, because that makes that lower, so more of them have it. And if we change concentration, pressure, or temperature, it means they're colliding more. Now, if we look at the rate equation, rate equals K times, the concentration of A, whatever, and then the concentration of B, and whatever, right? If we know that from the fundamentals, if you increase temperature, the rate of a reaction must be faster. If we change the concentration, then they also must be faster. Increase the temperature, more kinetic energy, more activation, more of them have the activation energy, and so forth. Increasing the concentration factors in the collision, right? So one thing, this is an example of what I mean by taking things at face value, because if you look here, it says rate equals K times concentration A, concentration of B. That, if we up any of these, well, then we know we're making the more collisions part happen, but if we increase the temperature, there is no T in this equation. There's no obvious T, right? So you need to think, why is there no T in this? That means it shouldn't work. However, if we look, we know that rate goes up with temperature, because we figured that out from before. This is not going to, concentrations aren't going to change the temperature. That's not going to change the temperature. So this K must be the only thing that has to change with temperature. Otherwise, this equation doesn't work, and the entirety of chemistry and rates doesn't work. But it does, so clearly that's the case. So then you need to think, how does K link to T? Well, that's what the Arrhenius constant is, minus EA over RT. That is, so the Arrhenius equation, that is your rate constant. That's what links the rate constant to the activation energy and the temperature, because now that fully explains mathematically why increasing the temperature does that to the rate. So it's really important important to take things at face value and understand just those little extra quirks, and that makes things a lot easier. So the rate of reaction 16.1 is carried out by 3 experiments at the same temperature, and the results are shown below. And that's also why they've told you that the temperature is the same, because that would screw up K. It says determine with the orders with respect to NO and CO, and the rate equation and the rate constant including its units. So what you've got to do is you've just got to look at experiments and see what happens. So here, between here and here, what we're doing, we're going from 2.7 to 5.5 because my mental math is horrendous. That's what times 2. So here we're doubling this. What's happened to the reaction rate? All you do is you divide that by the second one and see what happens. So 7.4 times 10 to the minus 4 divided by 1.85. That's gone up by a factor of 4. So therefore, if you increase the concentration of NO by a factor of 4, the rate increases by 4. Therefore, the order with respect to NO is going to be second order. What that means is that the rate is proportional to the concentration of NO squared. So if I double the NO, then the rate's going to go up by a factor of it squared. So we've figured that one out. Now all you do is you pick another experiment and compare them as well and see what happens. So the only one where CO changes is here. So what's happening from that to that? So if you do 2.9 times 10 to the minus 3 divided by 7.25, we can see that that is, 2 times 10 to the minus 4, that has been times by 4 to go up that way. What's happened here? 1.10 times 10 to the minus 3 divided by 5.5 times 10 to the minus 4 gives us times 2. In experiment 2 and 3, we're doubling, so NO is times 2. Therefore, the rate should also go up by a factor of 4, because we just figured that one out, right? So if we compare what happens with the rate then, so 1.18 times 10 to the minus 2 divided by 7.4 times 10 to the minus 4, 1.18 times 10 to the minus 2 divided by 7.40 times 10 to the minus 4 gives it's gone up by times 15.9 blah blah blah, which is like times 16 essentially. So the rate should have gone up by 4, but the rate's actually gone up by times 16. We know that the NO has contributed, so the NO has contributed a times 4, so it's times by something else to give us your rate times 16. So 4 times something gives us 16, so that X must be 16. Therefore, the only thing that we changed that wasn't the NO was the CO. So the CO times by 4 has times the rate by 4. Therefore, the order with respect to it, CO, is 1. So your rate equation is going to equal rate equals K times the concentration of NO squared CO, right? And then we need to work out the units. So so if we rearrange this, and they also want the K as well, K would equal rate divided by the concentration of NO squared over CO. You just pick any equation you want to do it with, so I'm just going to use that last one. So it's going to be 1.18 times 10 to the minus 2 divided by the NO, so that's what, 1.10 times 10 to the minus 3 squared, and then 2.9 times 10 to the minus 3. If we do that, that gives us 1.18 times 10 to 1.18 times 10 to the minus 2 over 1.10 times 10 to the minus 3 squared times 2.9 times 10 to the minus 3. That gives you, I'm going to put it in standard form, 3.36 times 10 to the 6. I've done a bit of rounding, but it works out to be 3.37. I've just rounded a bit lazily. And the units, if we look, we're going to deal with rate. So that's in moles per decimeter cubed per second divided by moles decimeter cubed squared times moles decimeter cubed, right? Tidy this up a bit. Mole decimeter minus 3s minus 1 over mole decimeter minus 3 cubed, and then 3 times 2. You add the indices when you're timesing them, so cubed. So that's going to be moles per decimeter cubed seconds to minus 1 divided by moles cubed dm minus 9, because you're timesing those now. And then it would be, the units would be, we usually put the negative not negative ones at the start. So it would be dm 6, because minus 3 minus 9, when you're dividing them, you're subtracting them, is 6. And then it would be 1 minus 3, which would be mole minus 2 s minus 1. So then it would be dm 6 mole minus 2 s minus 1. You usually put the positive one at the start, but it doesn't have to, you can put in any order usually. So now it says carbon monoxide also reacts with nitrogen dioxide in this reaction. It tells you the rate equation is shown below, suggests a two-step mechanism, and the first step is slower than the second. So if it's slower, it means it's the rate determining step. The rate determining step means it's the thing that's limiting how fast you can go. You can maximize absolutely everything else, but if this reaction's going slow, then the whole thing slows down. And an example of that, for example, is some medication. So for example, some medications, they're added, you put them in your body and they've got this extra thing on it, and it can't work until that extra thing is broken down. done. So that's purposefully there because it's rate limiting. What it means is this thing can't actually work until that's broken off. So no matter how much of this you have, does not matter, because as long as that's not broken down, it will not work. So you have to wait for this one to finish and then it works. Same with the concept of the rate determining step, is that no matter how much you max out absolutely everything else, it can only go as fast as that mechanism. Until that step's done, nothing else can happen. So that means if it's a rate determining step and they've told you the rate equation, it must mean that this rate, whatever's in that rate equation, has to be in the rate determining step, because again, that's the thing that determines the rate. So it says suggest a two-step mechanism. I told you the first one's slower. That means that this thing has to appear in the rate equation like that, NO2, and its power is the number of moles. You cannot have anything else on the left side, because if you added something else, like I don't know, something like H2 or something, then it should be in this equation too if it's the rate determining step. Therefore, any rate determining step can only have what is shown here on the reactant side. If that's the case, we know that we're starting with 2NO2. So I know that this is going to make something, and then this stuff, one of these might be the product, and the other thing comes in here. So we've dealt with the NO2 there. I'm going to put the CO in this next equation here so that we make sure that's reacted. Now, remember that we can only make NO and CO2 here, so you just got to think of possible ways to do that. So I know this one's probably going to make CO2, and I need to think what molecules can I get out of this that could react with this stuff to make the rest. So if I have a think, what I might try and do is I might do 2 NO, because we've got 2 N's, 2 NOs. I'm going to just pull out an oxygen, right? So now we have an NO there. We're happy, right? However, we can't have anything that isn't these basically reappear, all right? Because otherwise it would be in that equation. So this O2 has probably got to react with it. So the CO plus the O2, and maybe like CO and the O2 could make CO2, but then if we do that, it won't add up, because no matter how many times I up the COs there, it won't make a CO2. So I need to, because if I do 2O2, 3O2, 4O2, whatever, we'll still have some leftover oxygens. And oxygen is up here. So I need to figure another way to get rid of oxygen. And you're allowed to have that again, because it's still there. So what I'll do is I'll react the NO, and that can swallow up some of that extra O2. So we'll make NO2 plus CO2. It's a really janky way, but you have to look at it very literally. All you see are these things. So overall, when you combine these steps, it can only make those things in there, nothing else. So now it says this question's about energy changes. Magnesium reacts with aqueous silver nitrate as AgNO3 as shown below. So you got Mg solid plus aqueous AgNO3 makes silver solid, and then MgNO3 aqueous. And they've told us delta H for this reaction is minus 678 kilojoules per mole. When you're doing enthalpy changes or energy changes, don't just say, oh, heat's lost to the surroundings and stuff like that. Think about where the heat is going from and to. If it's exothermic, it means that this reaction is releasing energy into the environment, right? This delta H here for this reaction. If it was positive, so it's endothermic, it means that this whole reaction is taking in heat energy from the surroundings, and that makes the temperature go lower or higher, right? It's just really helpful to do it that way. They've told you a student adds an excess of magnesium to this much AgNO3 and the initial temperature is 20 degrees Celsius. Give the maximum temperature reached in this reaction and then your answer to 3 significant figures, and then assume that the specific heat capacity and density of the solution are the same for water, and assume that there's no heat losses. Right, so in here, we're talking about working out enthalpy changes in the laboratory, and the only way you can do that is by calorimetry, which is Q equals mc delta T, right? So Q is the energy release in joules. The M is the mass of whatever receives or loses heat that you're measuring. So what I mean by that is it's not the mass of the substance, it's not the mass of anything like that, it's the mass of the thing that's going up or down in temperature. So if you're doing calorimetry and you're burning a fuel, for example, you're setting fire to a fuel and the heat's going up here, it's not the mass of the fuel, it's the mass of what's having the temperature changed, which would be the mass of the water there. That's what people make mistakes on quite a lot. And then delta T is just the temperature change itself. Delta is generally changing, so that's temp change. So here you need to think, what's actually having the temperature measured and changing? The initial temperature, blah, 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 whatever, right? They're measuring the temperature of this reaction mixture. So here it's going to be, M is going to be the reaction mixture, not the mass of the, any of these things, if that makes sense. So if that's the case, they've told you that the specific heat capacity and density of the solution are the same for water. Specific heat capacity, sorry, I should have said, is the amount of energy needed to raise this by 1 degree per gram per kilogram, depends what it is. So the specific heat capacity of water is 4.18. They've told you that the density of this is the same as water. So the density of water is 1 gram per centimeter cubed. They've told us you've got, where are we? 100 centimeters cubed of this. So the mass of that solution mixture that's getting the temperature change happening to it is 100 grams. So if Q equals mc delta T, well, let's work out delta T is. They've told you that this initial temperature is 20. So the change in temperature is the temperature end minus the temperature at the start, which is 20. So we now know that Q equals mc delta T, so Q would equal 100 times 4.18 times the end temperature minus 20. We're a bit stuck though, because we're like, what the hell do we do there? This is where it gets a bit more funky, because we've got the enthalpy change of this reaction. Delta H is always measured in kilojoules per mole. Kilojoules of energy per mole of substance. And they've told us that that's minus 678, right? We need to actually figure out what that is, the enthalpy change in relation to, like, what moles are we using here. This is since they're adding magnesium to AgNO3 aqueous, the AgNO3 is the bulk of that stuff, and that's what the AgNO3, that's what the enthalpy change is attributed to. So what we need to do is we need to work backwards. It's a every mole of this will release minus 678 kilojoules of this. We need to figure out how many moles we actually have of the stuff. So the moles of AgNO3 is going to be concentration times volume, so 0.400 times 0.1, which is going to be 0.04 moles, because I divided that by 1,000, right? So what we now know that specifically in our example, the amount of heat energy released is minus 678 times 0.04. If we do that, then 678 times 0.04 is going to be 27.12. However, this is the enthalpy change in a kilojoule per mole. So for every mole of that would be that, but can you see how you have two lots of it there? So we actually have to divide it by 2 so we can get it down to what every single mole of that's releasing. Every single mole of that then is releasing 13.56 kilojoules of energy. Want to change it to joules? Then you get 13560. 13560. Look at my mental maths, joules. Sorry, rewinding a bit, just to make this a bit tidier, I should probably just left that as delta T, right? So that means that this 13560 joules equals 4.18 times 100, so that's going to be what, 418 delta T. So that means delta T is going to equal 13560 over 418, so 13560 over 418, which is 32.44. Is that what the question they wanted was? Maximum temperature reached, right? So if that's the temperature change, that means that delta T, well, that's, remember, the end temperature minus 20, which we've now just worked as 32.44 equals your end temperature minus 20. So that means that the end temperature is going to be 32.44 plus 20. And that makes sense because that's the change and it's gone up and it's positive. So the end temperature is going to be 52.4. Stick to the number of significant figures that they've either given you in the question or told you. So 3 significant figures, 52.4, 52.4. The student wants to repeat the experiment, but there's not enough AgNO3 left to use another 100 centimeter cube portion. So what they do is they instead modify it to add an excess of magnesium to 50 centimeters cubed of 0.4 moles per decimeter cubed AgNO3. Predict with assumptions what would happen to this to the maximum temperature reached, and assume there were no heat losses. In the previous part of the question, they told us that they used 100 centimeters cubed of 0.4 mole per decimeter cubed. So the moles of the AgNO3 before was the moles before was 100 times over 1,000 times 0.4, so it was 0.04 moles, right? Now the moles now is going to equal the moles now, sorry, is going to be 50 over 1,000 times 0.4, which is the same as just doing let's just do that now. So 50 times 0.4, which gives us 0.02 moles, right? So the enthalpy change before that they gave us was, where was it on the question? Minus 678 kilojoules for every mole we had. So every single mole, we gave out that much energy, right? So they've told us now, sorry, that we've now got half of the moles. So in theory, this delta H should be halved as well. Because every single mole of this AgNO3 gives you 600 minus 678, but now we've halved this. So whatever this was, that gave you that, must have been half of that. Now, the thing is, though, is that we need to factor in the fact we changed the volume too, because Q equals MC delta T, right? So the energy change we've just said would change. It would be a half, right? We've said because it's the half of the energy released because of the enthalpy change is now halved. So that means this Q should have also halved. But the thing is that we're also changing the mass that's having the temperature measured, the mass of the volume here, right? So that means that this has also halved as well. Essentially, these two effects cancel themselves out, and well, C is a constant. That's the energy change for this new reaction, but the volume's also halved. So this delta T has to stay the same. So what happens is that the maximum temperature is still the same, but we have half the energy release and half the volume. Which makes sense because even though we're releasing less energy, like half as much, we're also heating half as much volume. So it means you don't need as much energy anyway. So the effects cancel out. So the calculation also shows that too. So now it says nitric acid is made from ammonia in a multi-step process. And the equation for this first stage is in this equation there. It says some standard enthalpy changes of formation in this table. Explain the enthalpy change of formation. So it's the enthalpy change when 1 mole of a substance is formed from its constituent elements in the standard states. Now it says calculate the standard enthalpy change of formation of NO. The amount of times people will be like, okay, it's formation, so that means the arrows go up and down, like, actually makes me want to pull all of my hair out, eat it, and then like jump off a cliff, and then like go to hospital, and then do the whole thing again about 3 times. You cannot decide where the arrows go until you decide what goes on the bottom. It's not I see formation, arrows go up. It is I see this, I need to figure out what I'm drawing and actually think for a second and not just be like an absolute brainless, freaking. Okay, so what I mean by that is they've given you this equation, they've told you the enthalpy change. As long as you start and finish here, the enthalpy change should be the same. That's what Hess's law says. So write out the overall equation that we're looking for. NH3 gas plus 5O2 gas goes to 4NO gas plus 6H2O liquid. All right, and they've told you that the enthalpy change for this reaction here, whatever this reaction is minus 1172, right? When it says find the enthalpy of formation, that doesn't mean you jump straight away saying, oh, arrows upwards, because it's looking for the enthalpy change of formation of NO, and there's no NO here. So what are you going to do? Well, I mean, there is, sorry, but like, what are you doing, Like, look at the table and look at what they've given you. The table's given you enthalpies of formation for these two. Enthalpy of formation is always where you make 1 mole of a substance from 1 mole, sorry, not 1 mole, from its like elements in their standard states, right? So you're going from elements to the 1 mole of the substance. The next thing you do once you identify this is look at what's in the table and in the equation, figure out which side of this is. This is the 1 mole of substance, right? It's not going to be elements. This is made of N2 and H2. Here, that's your substance as well. So what it probably is that there's an element down here. So you're going to write your N2s and your this is and your that's, right? To decide which way the arrows go, it depends on what the enthalpy is, the enthalpy change. So it doesn't mean formation goes up. You're going from elements to this thing here, the substance. So it's going up this way. You can't go from elements to elements, so there's no enthalpy of formation. This is from elements to here, so that's formation, and then it's elements to H2O, like that. If it was the other way around, if the arrows went down, you are breaking down NH3 into its elements. That's the bond enthalpy. The reason this matters is because I've seen so many people absolutely fumble the bag with just the most strange cycles known to man. For example, it might say find delta H formation of ethanol using, I don't know, table 3, right? And table 3, I don't know why I said 3. What table is that? I'm going to say 3. Table 3, right? So here's your substance. Sorry, that's supposed to say 3. Here's your substance. That's your delta H that they've given you, and they've given you CH2 and then C2H5OH. And I'm making these numbers up, minus like 700, minus 300, minus 1000. Making it up. So find the enthalpy change of formation for ethanol. The amount of people that are like, okay, formation up. You do not know which way the arrows are going until you've written the whole equation and decided what goes on the bottom. End of. No matter what. If you're complaining, I've said this before, if you're complaining about learning these definitions, you're doing this whole topic wrong and you don't know what you're doing. Enthalpy of formation is the reaction that they want, which is here, which is 1 mole made from its substances and it's in their standard state. So that's 3H2. And then we've got what, like a half O2 here, right? It says find the enthalpy of formation of ethanol. That is the enthalpy of formation of ethanol using table 3. In table 3, they've given us the enthalpy of combustion. That's where you fully combust 1 mole of a substance in oxygen completely. So, here we're fully combusting this thing and this thing and this thing. So what we're going from is we're going from a substance to its combusted products. Right? So then what I said before is you look at the table and say, is this my 1 mole of substance or is it the combusted products? That's your 1 mole of substance. That's your 1 mole of substance. That's your 1 mole of substance. And they're being enthalpy combusted into the products. That's your 1 mole of substance. That's your 1 mole of substance. You can't combust oxygen. That's when you're 1 mole of substance. So that must mean the only other thing that can go on the bottom has to be the combusted products. And then you need to decide which way the arrows go now. This is the enthalpy change of combustion. We go from a substance to combusted products. So you're combusting this to make the combusted products. You're combusting that to make combusted products. So the arrows go down. This is being combusted as well. They've given you the enthalpy change of combustion for it. So that also goes down. That's how you decide the arrows every single time, because they'll give you an enthalpy change you're unfamiliar with. And you'll be like, oh my God, I don't know what to do. If you do this every single time, as long as you don't put the numbers in wrong in your calculator, you will get the marks every time without fail. This genuinely makes me want to like jump off a bridge that people don't do this and don't get taught this. I don't give a dang about your upwards arrows, downwards arrows and stuff because they can give you loads where it doesn't help. Here's another example where I see literally every person I've ever taught fumble this. I don't think I've had a single pupil do this right. So I'll say find the enthalpy of solution of NaCl using table 1. And so here's table 1. And let's say this is what they give you. I'm making the numbers up again. Right, that's all you get. And then people are like, oh, so do I need to do this? Do I need to do that? All the information is here for you. This is where the definitions are massively important. It's not memorizing them, it's actually knowing what the hell they actually do and mean and the purpose of them. The enthalpy of solution is where you have 1 mole of a solid ionic lattice, you dissolve it fully, blah, 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 and eventually you end up with aqueous ions. So this would be NaCl solid dissolved in water, delta H solution into Na plus aqueous, and then Cl minus aqueous. So where's your precious little upwards arrow, downwards arrows now? What are you going to do? You're like, oh my god, I don't know. It's enthalpy of solution. Which way the arrows go? I haven't learned that yet. I haven't done the cycle for it. Is literally just do what I do, bro. Look, it's told you enthalpy of solution. It means you're going from a solid to an aqueous. The next thing with all the other ones is I look at the table and think, what they've given me. So they've given me the lattice enthalpy of dissociation for NaCl. The definition of that is where you get 1 mole of a solid ionic lattice, it dissociates into its gaseous ions. I don't sit and memorize these, bro, because I just use them and apply them and know what I start and finish with. So I have a solid ionic lattice, and it becomes its gaseous ion. If I look at these delta H hydrations, the enthalpy of hydration is where you get 1 mole of aqueous ions from gaseous ions. So that means that this is going to start off with gaseous ions, and you're going to form aqueous ions. So like with every single other question I've done, I look at what's in this overall equation and think, which part of the enthalpy definition do I have? Do I have the start or the finish? This is a solid ionic lattice, and if I look at my table, there's a solid ionic lattice here, and they both get enthalpy of lattice dissociation into gaseous ions. So maybe down here I could write gaseous ions, which would be Na plus gas plus Cl minus gas, right? Then if I look at these are enthalpies of hydrations. You start with gaseous ions and make aqueous ions. So if I look here, I have aqueous ions, but here I have gaseous ions. So that means that these two are possibly linked. If that's the aqueous ions, and I can see there's gaseous ions here, enthalpy of hydration, gaseous to aqueous, the arrow goes up, and this one also has to go up. And this one's being dissociated, and it goes down. And then you put the numbers in. You don't have to draw some funky cycle. You don't have to memorize like 2,000 different cycles. You can take a second to actually just follow this, and you'll never, ever get a question wrong on this. So please, for the love of God, do this. Don't memorize anything like, oh, its formation goes up. The only way you know which way the arrows go is the moment you decide what goes down here, no matter what. Whether it's formation, whether it's combustion, whether it's even some other new ones that they've not given you and you've never seen before. Because they know you do this and you get it wrong. Literally every single time. It's really, really annoying. Because it's free marks if you do it this way. So love of God, the only way you know when the arrows go is what you decide when you decide what that is, and this. If you don't do that, you can't do it. It's not what enthalpy changes in the question, therefore it's up. It's what the hell is down here. So if you track back to this question, I've done that same thing. The overall equation is this thing here. They've asked me for the enthalpy of formation of one thing. I need to look at the table. They've given me enthalpies of formation. These are where you make 1 mole of a substance from its elements. That is the 1 mole of substance part. So what fed into that is elements, like that, to make the enthalpy of formation. In my table, I have the 1 mole of elements, or 4 in this case, so the elements were here. So the arrows go up for this. In the table, it's the enthalpy of formation of H2O, so I know that that's elements to H2O, so that's up. And they want the enthalpy of formation of NO, so it's got to be elements of this going up, right? So then when we put the numbers in, standard enthalpy of formation, so we need to plug the numbers in. So NH3, remember the definition is where you make 1 mole of a substance from its elements, so this time it's going to be 4 lots of minus 46. And try and bracket it off like that because it makes life a lot easier. Then we have 4 NOs. Well, that's just going to be 4x. I don't know what that is yet. That's what we're looking for. And then 6 lots of H2O. So we're going to have 6 lots of minus 286. And that's this enthalpy change here. So if you start here and here, even if you go around here, you're still starting there and there. So that means from going here to here, that enthalpy change must equal every other single root that gets you eventually there. So that means that minus 1172 equals, and we're going against this arrow, so minus 4 lots of minus 46. That's why putting the bracket out there just makes it nice and easy, because it's either just a minus or a plus. And then we're following this arrow now, so plus 4x. And we're following that arrow, so plus 6 lots of minus 286. If I tidy that up, I get minus 1172 equals, so minus 4 times minus 46 plus 6 lots of minus 286. That gives you minus 1532 plus 4x. So then if I subtract, so if I do minus 1172 plus 1532, I get 360 equals 4x. Therefore, x would equal, x equals 360 over 4, which is plus 90 kilojoules per mole. Plus 90. You gotta put the plus there because it's an enthalpy change. If I say to you, my weight has changed from last year to this year, I don't know if it's gone up or down. But if I say it's changed from 70 to 60, it's gone down by 10. So my weight change is minus 10. Whereas If I said it's gone up, so it was 60 to 70, you know it's gone up by 10, so its weight change is plus 10. So that's why you should say plus or minus when you're talking about enthalpy changes. There you go. Gets me heated, this question, dude. Now it says carbon disulfide reacts with the dinitrogen oxide as shown in this equation. Standard entropy is shown in this table. And it says explain the term entropy. It's the measure of disorder in a system. And what that actually really means is the dispersal of energy in a system. So you could say that either. That's technically what it is. It's how's the energy spread out in a system. Energy in a system. So it says the free energy change of this is that. Calculate the enthalpy change in this reaction. So start off by thinking, okay, well, what's the formula? Delta G equals delta H minus T delta S. What do we have? We know the temperature is 25. We need to change that to Kelvin, so that's 298 Kelvin, add 273. We know that delta G is minus 2672 kilojoules per mole, right? And we don't know what delta S is. So delta S is your entropy change. So it's the entropy at the end minus the entropy at the start of your reaction. So in the entropy at the end is going to be, so delta S would be the entropy at the end. So at the end of this reaction, our entropy is what? 256, right? That's the 256 plus 4 CO2, so 4 214s plus 8 N2s, so 8 192s. That's minus the start ones, which is going to be, where's our start one? So 4 CS2. Where's that? So 4 lots of 151 plus 8 N2O, which is 8 220. Plus, and then, so that is that. And then I'm going to just work that out. So delta S equals, it gives you 284. But can you see, always remember that the units of the entropy is joules per Kelvin per mole. We're dealing with kilojoules per mole. So I'm going to change it, divide that by 1,000. 0.284. Whoops. 0.284 kilojoules per Kelvin per mole. Then, you know that delta G equals delta H minus T delta S. So that means that if you add T delta S to that side, you get delta G plus T delta S equals delta H, right? So then all you would do is you would do minus 2672 plus 298 times 0.284, and that will give you your delta H. So therefore, delta H equals that, tidied. So minus 2672 plus 298, 0.284, and that should give you minus 2587 kilojoules per mole. Done. So now student concludes that this is feasible at all temperatures. Explain whether this is correct or not. So the only time that you can have a reaction that's feasible is that when delta G is less than or equal to 0. So you need to look at the formula. Delta G equals delta H minus T delta S, right? So your temperatures, if it's feasible at every single temperature in the universe, then this thing has to be 0. So in our example here, what's this? So our delta H, well, where is it? So delta H is negative in our example. Delta H is a negative number, right? So that means delta G equals delta H, which is a negative, minus T delta S, right? So temperatures are always going to be positive if you're using the Kelvin scale. You don't have negative numbers. It's 0 to 273. Sorry, 0 is the lowest, then 273 plus whatever is in degrees, right? So that's always going to be a positive value. The thing that determines whether that's going to be feasible or not is your entropy change. If we look at our entropy change in this reaction, it was where? It's positive. So it was 284. That's positive. So no matter what, this whole unit is going to be a negative as well. So delta G is always going to be a negative value minus a negative value again. So it means that that is always going to be negative. If this was a positive, so if that was negative, sorry, because temperatures can't be negative, then this whole complex would become negative. But because there's a minus on it, that becomes a plus. So above a certain temperature, if it's high enough, that will then be outweighed. For example, if, I don't know, that's like minus 10, and that whole complex was like, I don't know, minus 2, but then if I up that by about 5, so that whole complex becomes minus 2, but there's a plus because of the minus minus. If I then up it by another 10, for example, you can see that stays as minus 10, that becomes 10. And if I keep it up in the temperature, then it might be like 15, and you can see it outweighs that. So look at it mathematically. If this is always positive and that's always positive, this whole unit stays positive, but that's a minus, so this thing's negative as well. So you just kind of describe it into words. So delta S is positive, delta H is negative, therefore delta G is always negative because T delta S is always positive. There you go. So therefore it is feasible at all temperatures. So now it says the table shows the first ionization energies for elements from helium, He to boron in the periodic table. So it says complete the graph for C, N, O, F, and then Ne. So the first ionization energy is where you start with 1 mole of gaseous atoms and then they get an electron removed from them from their outer shell and you get 1 mole of gaseous 1 plus ions, right? So all of these are having their outermost electron peeled off. So have a think about what's happening with boron, carbon, nitrogen, oxygen, and fluorine. So if we look at what's going on, From boron to carbon, what's changing is that it's got one more proton, but you're still in the same shell. So its ionization energy is going to climb up. Now then from carbon to nitrogen, it's also going to climb up again because again, you're only adding one extra proton, but we're still in the same shell. However, if we look at oxygen, if we look at nitrogen versus oxygen, nitrogen is what? P1, P2, P3. So it's, what's that? 2P3. Oxygen is 2P4, right? So 2p3 versus 2p4. So you need to remember that there's usually a little bit of a drop between groups 2 and 3 and groups 5 and 6. The reason is because if we look at groups 2 and 3, you can see there's a drop between these and these. It's because the outermost electron here is in, well, in this case, it would be 2s, I think. We just double check on the periodic table. It would be in, 2s. So that would be 2s2, but now we're moving into 2p1, because that's the outermost electron. That p orbital, the next one, has a higher energy than the 2s. So it's easily taken away that electron. That's why you get that dip. However, between groups 5 and 6, you're going from 2p3 to 2p4. What happens is that if we look at the outermost electrons in nitrogen, here, you've got singly filled orbitals in that p1 here. But in oxygen, you've got 1, 2, 3, they fill up singly, and then doubly there as well for the P4. So what's happening is those electrons are actually repelling them, and it actually makes it slightly easier to take away the electron from there. So you actually get a little bit of a dip there. And then beyond that point, it carries on just going back up again, like that. So that's where that dip comes from. So now it says, estimate the energy required to form one Li plus ion from one Li gas atom, and then give your answer in kilojoules and standard forms from one significant figure. So let's have a look what's going on here. So we are making one Li plus G ion and that. So all we got to do is we can see that we have, if you look at lithium, its first ionization energy is 500 kilojoules per mole, right? The question's asking you for one ion though, right? This is one whole mole of them. So we need to divide that by Avogadro's constant, because remember, a mole is 6.02 times 10 to the 23. So if you do that, you get 500 divided by 6.02 times 10 to the 23, and that gives you 8.3 times 10 to the minus 22 kilojoules. So make sure you really read the question carefully and understand that a mole is literally just explain why the first ionization energies of He and B are both higher than the first ionization energies of lithium. So if we look at helium and beryllium, so helium, think about what's going on. So we are peeling this electron away from 1s2, and here we're peeling it away from 1s2 to s1. We've entered a new shell. So for helium, there is increased shielding as the electron is in lithium is removed from the next shell. So there's less attraction between the nucleus and that electron, so less energy required. So stop saying atomic radius and this and that garbage. You need to describe what that means. I don't like people who just jump to saying atomic radius because you don't get marks, or they just jump to saying it and getting it wrong. And it's just a bit annoying. Now, here it says, why is it beryllium is higher than lithium then? So beryllium's higher. So if we look at between lithium and beryllium, 1s2, 2s2, 2s1, 1s2, 2s2, right? We're not jumping into a new shell or going down a shell, so why is it going up? You need to compare them directly next to each other, Li versus Be. So we can see that Li has, 3 protons? Beryllium has 4 protons. The only difference between these two, other than the extra electron, is the protons are different. Everything else is the same. So therefore, you've got a higher number of protons, therefore you've got increased nuclear charge, therefore that increases the attraction between the outer electron and the nucleus, and that leads to decreased atomic radius. It actually decreases in size because that electron's been pulled in closer, and also that means you've got more energy needed. There you go. So now it says explain why the first ionization energy of beryllium is higher than that of B. Well, I've actually just boron. Well, I've just done that because in beryllium it's 2s2, and then boron is 2p1 after. So 1s2, 2s2, 2p1. Right now, that orbital has a higher energy. So in boron, the outer electron is in 2p, which has higher energy. Therefore, it's easier to remove. So it's higher energy than the 2s orbital. That's why we get that drop. So this question's about acids and buffers. Succinic acid is a weak dibasic acid that is used in tablet form in health supplements. A student plans to determine the mass of succinic acid in a tablet and succinic acid health supplement. They carry out a titration with potassium hydroxide. So when you're doing titrations, in any titration question, it's a back titration or anything like that, don't just say this was titrated with this. you in your head think about what's being mixed with what, as in this is going to be mixed with this, and then they react, because it's so easy to just be like, oh, it's hydrated with this, and then no one knows what's going on. Think about it, what's in the burette, what's in the beaker, like that. The endpoint is when both of these have been replaced. Both of these protons in succinic acid have been replaced as shown. So you've got HOOC, so you should be able to recognize that's a carboxylic acid group, and there's another one there, so it's a carboxylic acid group. So you've got dicarboxylic acid, adding your KOH, and then you make a salt plus water. Acid plus base makes a salt plus water. Every single acid-base reaction will do that in the entirety of the universe. So then it says the student uses the following method. The student crushes 4 tablets of this supplement, dissolves them in distilled water. They make up a solution from stage 1 to 250 centimeters cubed in a volumetric flask. From that big-ass volumetric flask, they take 10 little bits out and titrate it with some amount of potassium hydroxide, and they use phenolphthalein as the indicator. The student carries out a titration reaction in the following titrations. The results are shown below. So the amount of people that do this question, and they're like, oh, I need to work out moles, and they do like, I don't know, this times that. Each one of these, you need to know exactly what it belongs to and where it's come from. So what I mean by that is that this 10 centimeter cubed is the amount of succinic acid that they took away from that volumetric flask. This is the concentration of potassium hydroxide. So then you need to figure out what the hell those volumes are. What are all of those burette volumes? That's what I meant before by looking at the reaction, thinking what is what specifically. This is all must be from the question. They've told you they've titrated 10 centimeter cube bits of succinic acid with something else. That has to be those volumes of your KOH, right? So it's really important that you make sense of that. So to work out the titers of each of these, you just subtract them and what's so forth. So this is the trial titer. So it just put the numbers into 22.75, 22.455, 22.7, 22.55, 22.7, and then it says calculate the mean titer and then use the ones for the results. So you should use the concordant results, which are within 0.1 of each other, within 1 decimal place of them. So of those, it would be this and this that you're going to use in your mean titer. So it'd be 22.45 plus 22.55 divided by 2, and that gives you 22.5 centimeters cubed. Now, when you're doing this, like I said before, don't just do, oh, I'm going to work out moles and this and that, blah, blah, blah. This is the volume of the KOH that reacted with 10 centimeters cubed of the acid. If you're going to work out moles of something or use a quantity, you need to know where it belongs to and what you're going to do next with it. If you don't, then you don't know what you're doing, and you're going to get every single one of these wrong every time. So now it says use the information in the results in that equation to calculate the mass of succinic acid in 1 tablet of this supplement. So make sense of what they did. They got 4 tablets and they dissolved it in 250 centimeters cubed. Then what they did is they reacted 10 centimeters cubed of this with the 0.06 mole DM minus 3 KOH. What volume of that? That's the volume of the tablet of the succinic acid, because that's the only thing that in it that's going to react. What about the KOH? The titration that they did, the amount that it reacted with was 22.5. So 22.5 centimeters cubed of that. Okay, cool. That's it. That's all they did. We want to work backwards to get that 4 tablets. All we know is this information here. So then people jump straight into making moles and this and that, and they have no idea what's going on. And then they're like, oh, I'm getting everything wrong. Why do I always keep doing this? If you're going to work out moles, you need to be able to justify every single step. So I can see that whatever's in these tablets is going to react with KOH. And the only thing that it can be is the succinic acid. So the moles of the KOH reacting, the reason I'm working it out is because then I know that that's only reacted with succinic acid in this equation from the question they told us. I can work out the moles of that. So the moles of the KOH is going to be its concentration 0.6 times 0.06 times 22 over 1,000, which gives me 1.35 times 10 to the minus 3 moles. I know that this is only reacting with succinic acid, which is in this equation here, which is that. So therefore, your moles of the succinic acid, I'm just going to call it acid because I'm a bit lazy right now, that is going to be this answer divided by 2, because there's a 2-to-1 ratio. So that means the moles of the succinic acid is 6.75 times 10 to the minus 4 mole. Now, people jump and be like, okay, therefore, the mass equals moles, blah, 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 whatever, right? Use your common sense. Think for a sec. So I always do this. I always force myself to just say that in 10 centimeters cubed. Then I know for a fact I need to go backwards. And I always write a little flowchart too. So the moles of the acid into 50 centimeters cubed has to be, well, you're going up 25 times, 250 over 10 times this answer there, right? So that actually means you've got 0.016875 moles in 250 centimeters cubed, right? So that's how many moles of the acid it is. All this acid must have come from where? Give it a second pause and have a think. All of that acid must have come from those 4 tablets. Therefore, the volume of that 250 is irrelevant at this point. I know definitely for sure that the moles of acid in the tablets, the 4 of them, is going to be that 0.016875. So that means that the mass of the acid in the 4 tablets is going to equal the moles 0.016875 times the MR of the acid, which in this case is going to be 118. So now I know that the mass of the acid in 4 tabs is going to be this thing calculated, which is 1.99125 grams. Therefore, 1 tablet must have that divided by 4, which gives us an answer of 498 grams, 0.498 grams, whoops. And they want in milligrams, so you got to times it by 1,000 to get 498 grams. You need to, milligrams, sorry. In all of these questions, you cannot just jump in and randomly work out moles, or you'll get it wrong every time, and they always do this. It's reading comprehension. If I say, all cats are animals, cats have 4 legs, you cannot say, based on that, okay, every animal in the world has 4 legs. It doesn't. Right? I could say centipedes are insects and they have however many legs a centipede has. That doesn't mean every insect in the world does. It's reading comprehension. You got to understand what's reacting with what. As in, which part is this being explained by? Which part is that being explained by? The concentration of volume, concentration of that is there. Its volume is this stuff because you have to imagine the reaction happening. This is only 10 centimeter cube bits because I've only taken that out. We don't, and you know, so we don't know its concentration, so we can only use the moles of this to find this. It's really important you do that. I absolutely can't stand it. It's another error that I see people do where they just kind of blindly just calculate anything and see what happens. Next, it says glycolic acid has a pK of this, and it's a weak monobasic acid. It's used in skin care products. A buffer solution is made by adding this much glycolic acid to this much potassium hydroxide. Explain why a buffer solution is formed. So here's what my question to you is: what makes an acidic buffer? What at its fundamental level, what is an acidic buffer? No matter what, if you had to describe it in one sentence. All right. So you probably said something like, "Oh, it can resist pH changes. Every buffer in the world can do that." I want to ask, what makes an acidic buffer? The reason buffers work is because they use those equilibria and shift. It is all just equilibria again. So in order for the equilibria to actually be relevant, it has to be a weak acid because strong acids nearly fully dissociate. So fundamentally, it is a weak acid mixed with, and it has to have lots of A minuses. A minus comes from salt. So it's literally just anything that's where you've got a weak acid and it's salt. So sodium ethanoate and ethanoic acid. That is it. Any acidic buffer in the world. A basic buffer is the same thing. Any weak base, which would be ammonia, mixed with its salt, ammonium chloride. If you have those two things, you have a buffer. So then you need to think of ways of making this. So you have a think and tell me. There's 2 ways. You could obviously just do weak acid mixed with its salt. But what you could also do is you could just add some weak acid, but make sure it's in excess, and you can add a strong base. All of that strong base is going to react with the acid and make a salt. But because you've got excess acid, what's left behind is a weak acid and its salt, which is a buffer. So if you ever have a weak acid and a salt that it makes, you have a buffer by definition. So explain why a buffer solution is formed. Well, it's because here, I mean, you should be able to, even if you didn't even know how to calculate it, the glycolic acid is in excess and all KOH reacts to make a salt. Therefore, it is a mixture of weak acid and salt. Therefore, you've got glycolate ions produced, or A minus ions, or something like that, or like you can write the equation so it'd be like HOCH2CO minus. That's quintessential. Right, so it says now find the pH of a buffer solution that's been prepared. So if you want to look for pH, you need to find H+. Can't do it without. So then you need to think, okay, I need to find H+. What options do I have? KW says H+ and OH-. Yeah, that helps, but OH- is whenever you have a base that represents base. So we're out with this one. This doesn't help. Anything that's basic will be useful here. Our other option is to just be like, oh, well, I mean, surely it's the same as the acid. But this is a weak acid, so it doesn't fully dissociate, so that doesn't help us either. The other options are our Kas. Now, there's 2 Kas. There's Ka equals H+ squared over HA, or Ka equals H+ A- over HA. You need to understand what all of these represent. H+ is what we need. HA is the concentration of the acid. So what's A-? That is the concentration of salt. So coming back to the absolute basics, if this has no A- in it, I don't see an A-, there is no salt. But I see an HA and an H+, and weak acids do that. So therefore, this is only if you have only acid, no salt. Whereas Ka, H plus A minus, we've got the acid there and it's salt. A minus has this A minus there, so salt is there. So salt plus acid, as in our buffer. That's how you recognize which ones to do. So we need a pH. We're going to be using Ka. Let's collect what we know so far. So we know that Ka, well, they've told us pKa, so Ka would literally just be 10 to the minus 3.83. That is all. That's all we know. So we need to find A minus and HA, and we can find H plus. The problem is again, think about what's happening in the reaction. We are mixing this acid with a base. Acid plus a base will always make a salt plus water. So some of it's going to react. We need to figure out how much is left after the reaction to do this. So whenever I do an acids and bases question, even if they're not reacting an acid and base together, I always do this because it means I never, ever fail. I write out a basic, just quick thing about this. So I'm saying that HA, the acid, plus a base, which is some form of OH minus usually, makes a salt, which is going to be A minus plus water, which I don't really care about because we don't care about it because there's no H2O there, so it does not matter, right? So then I do what before the reaction, after the reaction, the moles before, sorry, the moles after, but then this requires concentration, so then I do the concentrations after the reaction. If you do that with every single question, even if they're not mixing two things together, it makes a lot more sense. So then think, we're reacting glycolic acid and this base. So the moles of the glycolic acid before you've actually done any reacting is going to be that 0.750 times 60 over 1,000, which is going to be 0.045 moles. The amount of base we've added is going to be the volume, so 40 over 1,000 times 0.625. So if we do that, we have 0.025 moles. So then my next question to you before I tell you is, how much salt do we have at this point? No trick questions, look at it very face value. Before this reaction's happened, we have 0. So we can't actually use that. And technically speaking, almost looks like we'd use that. But they haven't reacted yet. Water, don't care about, but I mean, it's 0 there as well if we're going to assume that. After the reaction, think about what's happening. This acid is going to react with this. So if it reacts with this, they're both going to drop in numbers. The only thing that they're going to make is either the salt and the water. I don't really care about the water again. So we need to figure out how much salt we make. We have more acid than there is base. So all of this base is going to react while some of this acid is going to be left over. If that's the case, then we can only make as much salt as there is base because that's the limiting reagent. There's only a little bit amount there. So that means after the end of the reaction, we will have 0.025 moles of the A minus. At the end of the reaction, we have no base, and that makes sense because I don't see an OH minus there. It's a good thing. It matches that equation. And then here, that's going to be these two subtracted, so we're left with 0.02 moles. Now what we need to do is work out the concentrations after. So concentration, remember, is the moles over the volume. But because we mixed two solutions together, our volume now is going to be 100. So now the concentration is going to be 0.02 divided by 100 over 1,000. And that's going to be 0.002. And then that's going to be 0.0025. Right? And that's our concentration of our acid. That's our concentration of our A minus. So now we have our Ka. We have our A minus and HA. We need H plus because remember we're looking for pH. So Ka, always rearrange algebraically first, then put the numbers in. So Ka times HA divided by A minus will give us our H plus. So therefore, H plus is going to equal our Ka, which is 10 to the minus 3.83 times the HA, which is 0.002, all divided by our A minus, which is 0.0025, which is going to equal give me a sec, 10 to the minus 3.83 times 0.002 over 0.0025, 1.18 times 10 to the minus 4. Obviously, still write more decimal places, I'm just being lazy, then negative log to the base 10 of that, because pH is negative log base 10 of the H plus. That gives you 3.926, which is roughly 3.93. You should do it to two decimal places. If you do this in every single acids and base question known to man and its buffers, it will be easy. And it should be 3 marks as long as you're not putting the numbers wrong in your calculator. Even if, for example, it said they mixed an acid and the salt, same shtick, to be honest. If you force yourself to just follow it like that, HA, OH minus, goes to A minus plus water. It's a one-size-fits-all method. Acid, base, salt, and then that. Start, end. So the question might say, oh, they reacted a thing with a salt. The moles of this acid would be whatever the moles of it is, whatever the number is. Base, in the question, it hasn't said they've added any base. So nothing. They've told you there's some salt, there's going to be that. And water, there. If it's already here, they're not going to react, so the same will be at the end, and you just follow the same steps, and you'll always never fail. It helps you organize your thoughts, because these only work once all the reaction-y bits have been done. All of them, to be honest. So that's how you do any acids like buffer thing in the universe. So now it says a small amount of aqueous ammonia is added to the buffer solution. Explain in terms of equilibrium what happens. So think about what's happening. So we've made a buffer where we've got HA, and it shows you in the Ka equation, HA, A minus, and HA. But you can see as well, even here, we have HA and only A minus there as well. And it's obviously going to have some H pluses to get back up there as well, but that's not in there. So any weak acid equilibrium is eventually going to set up this A minus and H plus, right? So they've told you that a small amount of aqueous ammonia is added to this buffer solution. Explain in terms of equilibrium what would happen. So all equilibrium, well, remember that Le Chatelier's principle is that you make a change, the equilibrium shift to counteract the change. Now we need to figure out what happens to this equilibrium if we do that. If we add NH3, I don't see an NH3 anywhere here, so it's not going to make a concentration of this go up directly. However, NH3 is a base, which means it can accept a proton and react with an H+. So it's going to react with that. It won't react with the HA. It won't react to the A minus, but the NH3 will react with the H plus to form NH4 plus. So that means that the concentration of this H plus is now dropping because it's being passed on to here. So the equilibrium will shift to the right to make that go higher, make the concentration of that higher. So then that's exactly what happens, is that the NH3, or the OH minus, because the technical solution does that, but the NH3 reacts with the H plus from the acid, whatever it was called, glycolic acid, I'm lazy. You could even write this equilibrium, therefore, you should actually no, you should do that if you're going to do an equilibrium thing. So HOCO2COH, that's the actual HA, becomes H plus HOCH2COO minus. If you do that, this causes H plus to concentration to drop. Therefore, the equilibrium shifts to the right, not to counteract the change, to say what that change is, to increase H plus again. Can you see how that's how a buff that resists changes in pH? Because pH is entirely dependent on H+. If you add something and it makes it go down, and it goes, it shifts to make the H+ go either up or down again or whatever, that's resisting the pH change. That's how it works. This is literally all just application of equilibria. Again, same old story. So it should be 3 marks. And the same goes for KP, Ka, any K, literally anything. Like, if you just understand what's going on reaction-wise, this is doing this with this, it's fine. So then it says, here's a question about equilibrium with hydrogen. Hydrogen is used to industrially manufacture ammonia, and the equilibrium shown below. They mix this much with this in a container. So you know the previous question where I was rambling on about knowing how equilibria work and you always do start and finish? It's the same thing. Any acids and base question where they're reacting an acid and a base, it's literally the same as, oh, this was mixed with this. At equilibrium, this was this. It's the same thing. So here they've mixed these two together. The mixture is heated with an ion catalyst and allowed to reach equilibrium, and then this says what it has. So it says determine Kc and explain what operational conditions might be different to what they do in the, what the actual yield would be. So let's do the first part to figure out Kc. So Kc is going to equal, what are we dealing with here? So we're dealing with concentrations. I know they're gaseous, but they're giving you moles and decimeters cubed. So the Kc's are going to be, well, Kc equals NH3 squared over N2 times times H2 cubed. This is Kc. So all these are this is the equilibrium constant. So these are all concentrations at equilibria, right? Or equilibrium, sorry. These values they've given you here is right before the equilibrium has been set up. So we need to find the concentrations of all of these things at equilibrium to find Kc. So in the same way I was doing the acids and bases thing before, I write out the equation. So N2 plus 3H2 gives you 2NH3. And then I think what's happened at the start, or after the reaction, so at equilibrium, and then I work out the concentration. So these are the moles, and these are the moles. At the very start, they've told you that they're mixing 1.20 moles of N2 and 3.60 moles of H2. At the very start, do we have any NH3? No. However, when we hit equilibrium, when it's starting to go back and forth, eventually levels out, it's told you in the question that in the equilibrium at the end, it's 0.160. Now, that means these two have reacted in a certain amount to give you this. All of this NH3 has come from those two things. So this has gone up by plus 0.160. Since every one of these makes 2 of those, that means that this will have dropped by 0.08, half of that. So then at equilibrium, the amount of N2 left is going to be 1.12. every 3 of these makes 2 of those. So if that's dropped by 0.16, because we halved it here to get it down to the 1, we have to divide that by 2 to get it to 1, and then times it by 3. So it's going to be 0.16 divided by 2, and then times by 3. This will have dropped by minus 0.24. So that means at equilibrium, we have 3.36 moles of these. So now we have our equilibrium moles, but remember that one's equilibrium concentrations. So the concentrations are all going to be their moles divided by the volume, and they've told you the volume there. So it's going to be 1.12 divided by 8, which is 0.140. It's going to be 3.36 divided by 8 as well. So that's 0.420, and then this divided by 8 as well, which is 0.02, right? Now, remember, it's asking you to say what the equilibrium constant is, and we should always do units with it as well. So Kc is going to equal those numbers plugged in now, because those are equilibrium concentrations at equilibrium. So NH3 squared is going to be 0.02 squared divided by 0.14 times 0.42 cubed. And that gives us 0.0386. Its units are going to be mole dm minus 3 squared over mole dm minus 3 times mole dm minus 3 cubed, so it's over 4. So we're going to be left with mole dm minus 3 minus 2. So that's going to be moles minus 2 dm 6. And usually we put the positive one first. Is dm 6 mole minus 2. That's the first part of the, the question done and dusted. The next part says, explain why the operational conditions may be different for those that would get a maximum yield of ammonia. So to max out the highest yield possible, what would we need to do? So the forward reaction is exothermic. So the reverse has to be endothermic. If I wanted to go this way, if I want the equilibrium to shift to the right, I'm going to need to lower the temperature, because if I remember, Le Chatelier's principle means an equilibrium will counteract the change that you make to it. So if I lower the temperature, it's going to counteract the change and try and make the temperature go higher, which means it would shift to the right, because that is exothermic and make the temperature go up. So the highest yield known to, possible would be the lowest temperature you can get, right? That's that. What other conditions are there? So as well as that, they've told you, where are we? In equilibrium, blah, 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 blah. Oh, catalyst, there you go, right? Catalyst has no effect on the equilibrium. Fine. What else? They've told you the temperature, what they've done, fine, whatever, what else? What else is there? These are gases, so we need to talk about pressure. So again, if you make a change to an equilibrium, it'll shift to do the max you want. So you want it to make this much. You want it to go this way. So because there's 1 plus 3, that's 4 moles on this side, and 2 here, if you increase the pressure, the equilibrium will shift to decrease the pressure. Ideally, you want a high pressure, right? That's what the yield is. But then in the industrial scenario, what have they told you? Well, they've told you the temperature is 550. That's higher. So you need to think, why would I want to use a high temperature? That doesn't make sense. And we'll carry it on from there. Okay, so now we're at this point where we've figured out what maximizes the yield. We need to look at the possibilities in regards to like what the industrial actual reaction happens like. So with these things, it's great if we can make like a really high yield of something, but the problem is that businesses also have to sort of, make a balance between what they can and can't do. So with this kind of question, think about what's going on in the question in terms of what you've just found out, and think about what problems might come as a result if you're running like a business that tries to make this thing industrially. So in this question, we found that the highest yield would be if we had a low ass temperature. The catalyst is used for some reason, but it doesn't really have an effect. And if we have a really, really high pressure. So in that case, you'd want like nearly an infinitely high pressure, the lowest temperature known to man and whatnot, right? But they've told you that they do it at 550 degrees, which is not very low, an iron catalyst, but surely that doesn't affect the equilibrium. And like, there's not really much on pressure, so why might they use a temperature that's high? Well, there's no point making a nearly 100% yield of this if it takes like 200 years to get to it. If it's so slow at making this, there's no point. So that's why they use a higher temperature to get the reaction rate sufficient. But then the problem is if you use a higher temperature, it starts to go that way. So what they've done is they've added a catalyst, because adding a catalyst means you don't have to use as high of a temperature, so they can get away with using that, if that makes sense. Because then it means they can keep that, you can use as low of a high temperature as possible without making it go too much in the opposite direction. So here, why have they used a higher temperature? Well, it's because the high temperature increases the rate, but it's a compromise for yield. The catalyst, though, allows using a lower temperature, and that can at least increase the rate and lower energy consumption in heating it. in heating the reaction. And then, as well as that, in terms of pressure, well, if we use like a really, really high pressure, it's expensive to generate because you need a lot of energy to do that. Expensive and requires a lot of fuel, and is a safety hazard as well. Because if I like have this bottle that's got like a really, really, really high pressure, like a water bottle, it will just blow up. So we don't really kind of want that. So now it says, in industry, the hydrogen is also used to reduce iron oxide, as shown in this equilibrium. The reaction is carried out at 500 degrees Celsius. So then they've got this reaction here, whatever. It says when the temperature decreases, the value of Kp decreases. Determine whether the forward reaction is exothermic or endothermic. So Kp is basically just your, your products and all of that stuff, right, over reactants. So if Kp is going down, that's going down as well, and that's going up. Because those are the things that make Kp go lower. So whenever you change, so remember that Le Chatelier's principle is where you make a change and the equilibrium opposes the change, or wants to. So what happens is the change that they've made is they've decreased the temperature, and the change that it seems to have made, well, the change that it wants to make is that it's going to want to increase the temperature, all right? So you decrease the temperature, it wants to increase the temperature. Now, it's told you that Kp goes down, so it means we've got less products, more reactants. So this means it's shifting to the left. So if by shifting to the left it's increasing the temperature, the left must be the exothermic direction. So therefore, the forward reaction has to be endothermic, because if you were to increase the temperature, then it would try and decrease the temperature, and it would shift to the right, to the opposite. So that's what it would be. So it would be that the equilibrium shifts to left as the temperature drops. Therefore, the forward reaction is endothermic. So two students are discussing the effect of pressure on the equilibrium in the position of 22. Student 1 says there are more moles of products than reactants, so increasing the pressure will shift the equilibrium to the left-hand side. Student 2 disagrees. Which one's correct? So they're saying that there's more moles of products than reactants. If we look here, we've got 7 versus 5. So increasing the pressure will shift the equilibrium to the left-hand side. They're wrong, because if you take a more, a closer look, that's solid, and that's solid. Remember that these equilibria and all this pressure stuff only applies to whatever's in gases, and that's only gas there, and that's the only gas we have 4 moles and 4 moles. So actually, the increasing the pressure is not going to really do very much because there's the same amount on either side. See, that pressure stuff only applies to gases, and changing concentration will only apply to either gases or aqueous stuff. These solid things aren't going to make the equilibrium shift. The only way to do that is to add more solid in. Pressure's not going to really affect them because they're not gases. So student 2, because there's the same number of moles of gaseous reactants and products. So it says this question's about the reaction of group 2 metals and their compounds. A student adds magnesium to dilute hydrochloric acid in one test tube, and then calcium to another, and then a redox reaction takes place. What are the two observations that would show that calcium is more reactive than magnesium? So they've even told you calcium is more reactive. So you need to think what would happen, like what would you see, because it's an observation. So, with these metals, when you add them with water, they're going to start dissolving and sort of bubble. So there's already one. And as well as that, when you're reacting calcium with H2O, you're going to make CaOH2, and you're going to make something else. You're going to make H2 gas. So they're both making bubbles. One is extremely slow, the other one isn't. So that must mean that calcium must be fizzing or effervescing faster, because if it's more reactive, you've got to make a faster or comparative statement. You can't just say it's fast, you have to say it's faster. And also, it's dissolving as well, so the calcium will dissolve quicker or disappear quicker. Those are your observations. It's like what you're seeing. So now it says write half equations for the reaction of magnesium with hydrochloric acid. So if we just quickly sketch what's going on here, we've got magnesium plus HCl, 2 lots of that fine. We'll make MgCl2 plus H2, right? Now, we need to have a look at what is going on in terms of the ions. So magnesium is oxidation state 0 here, but then it becomes +2. So if it's done that, it's become oxidized. So that first equation is going to be Mg, becomes Mg2 plus, and then you've got to balance the charges on either side, and you also know that this has lost 2 electrons, so there you go. With redox, you have to think of it in terms of oxidation states, and also gaining or losing electrons. So then if we look at the oxidation state of the H here, that's +1, and then the Cl is -1. But here, you can see that the oxidation state is simply just... But the oxidation state for elemental hydrogen is 0. So that means each of these hydrogens has gone from +1 to 0. They've gained an electron. So you would have 2H plus 2E minus becomes H2, or you could do half of that. Either's fine. A sample of barium oxide is added to distilled water at 25 degrees Celsius, and then a colorless solution is formed containing BaOH2. The solution is made up to 250 centimeters cubed of distilled water, and the pH of this is this. Determine the mass of barium oxide that was used. So we're adding a hydroxide to water and its pH has changed. So we need to look at H plus eventually. So if we work out H plus, that's going to be 10 to the minus 13.12. Now, when you're adding a base to water, it disrupts that sort of nice H plus OH minus balance that water has, and that screws up your thing here. So what happens is you're changing the pH like we just figured out, but the thing that's causing it is because it's a base, it's going to be the OH minus. So that means we can try to work out what H minus is. So you need to think, what do I know that links H plus and OH minus together formula-wise? And that's Kw. Kw is H plus times OH minus, right? And they've told you it's at room temperature, so that means the Kw is 1 times 10 to the minus 14. So then the next step is when you're doing these calculations, you should always be able to justify what step you're going to do with it and why. So if I work this OH minus out, I need to think, where does that link to? Well, it's all coming from here. So therefore, I know that the concentration of H minus, which must have come from here, equals Kw over H plus, which is 1 times 10 to the minus 14 over 10 to the minus 13.12. If I do that, I get 1 times 10 to the minus 14 over 10 to the minus 13.12, which gives me 0.138257. Let's go with that. Right? And that's moles per decimeter cubed. Now, therefore, what else do we know now? So we know that the solution is made up with this much distilled water, so we can try and work out the moles of OH minus now, which would be the CV, which is just going to be that answer times 250 over 1,000. If I do that, we get 0.03296 moles. So all of that has come from the BaOH2, right? So if we look at what happens with BaOH2 in water, that will dissociate into Ba2 plus 2OH minus. We just worked out the OH minus. So this BaOH2 has a 1 to 2 ratio with that. So that means that the moles of the BaOH2 is going to equal your answer over 2. But then as well as that, this all came from dissolving BaO in water, and if we did write the equation for that, it would be a 1-to-1 ratio. So that means that the BaO moles, because that's what we're looking for, remember, barium oxide, is actually still also the answer over 2. So if we do that, the moles of the barium oxide is 0.016478, and then it's asking you for the mass, so mass equals moles times MR, which would be your answer times the MR, which is 153.3, which is 2.53 grams. There you go. So 10 centimeters cubed of dilute sulfuric acid is added to 10 centimeters cubed of this columnar solution. Write an ionic equation including state symbols for this reaction. So what's going on here is that we've got, just if you quickly sketch what's going on, so BaOH2 plus H2SO4 gives you, well, you were going to get BaSO4 solid plus H2O liquid, acid plus base makes salt plus water, right? Now if we're going to do an ionic equation, let's just break this into its ions. So what that means is we're going to have Ba2 plus 2OH minus plus, what's that, 2H plus SO4 2 minus goes to BaSO4 solid, because they're now solid as ions, and then H2O liquid. So you can't really do anything much more else of that. I mean, I guess you could probably go to 2 plus and SO4 2 minus, and then those cancel out, those cancel out, that cancel out, that cancels out. And you can be left with H plus OH minus gives you that. Have I balanced that? Yeah. So you would get H plus OH minus goes to H2O. They allow that. So H plus OH minus goes to H2O liquid. So that's one of the ionic equations you can go down. So because you're just canceling them all out. Sorry, 2, 2, 2, but I'm just going to keep it as 1 because you can simplify that down. Whereas you could also write that because that Ba goes from an aqueous to solid, you can keep that in as well. So you can have Ba2 plus 2H plus SO4 2 minus plus 2OH minus goes to BaSO4 solid plus 2H2O. It allows that as well, and it allows the multiples. The reason that works is because these are still solid. You can still, and those become a liquid. So they're still changing in phase. So you can include those as well. So now it says limestone and huntite are 2 calcium minerals. A typical sample of limestone has this much of calcium carbonate. Fertilizer Ca5NH4NO311.10H2O with the MR of this can be made from limestone. Calculate the mass in grams of limestone needed to make that much fertilizer. So I can't go into this unless I just quickly sketch what's going on calculation-wise, right? So if we look here, you can make this fertilizer using limestone. So I'm saying that you can use CaCO3, and eventually you'll land yourself with CA5 NH, blah, 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 whatever, the whole thing, right? So if there's one Ca here and there's 5 there, that means I'm going to need 5 of these going in. That's always a good start. So now it says calculate the mass of limestone needed to make this many 1.50 kilograms of fertilizer Z. So you can work out, but now that we have a very rarely scuffed equation for these two, you can work out the moles of this, then work backwards, and then do it like that. So is there anything else that we're missing in this question? So a sample of limestone contains 95% mass, right? So whatever we work out here is only going to be the theoretical thing, but we've got to remember that like that's only going to be 95% because we're going to have to put more of this limestone in as well, because not all that's only 95% of it. We'll factor that in later there. So if we work out the moles of Z, that's going to be the mass, which we're going to have to change it to grams, 1,500 grams, over its MR, which is 1080.5, and that gives you 1.388246 moles. Right? Now we can see that there's a 5-to-1 ratio, so that the moles of the CaCO3 has to be 5 times the answer. Now if we do that, we get 6.94123. Remember that this is if the reaction was perfect and these both added up and did everything perfectly fine. So that means our mass of CaCO3, according to this equation, would be 6.94123 times its MR, which is 100.1. If I do that, I get 694.8 grams. However, the questions told you that a typical sample only has 95%. That is 95%, because only if you had a typical sample of limestone, only 95% of that mass is actually the actual CaCO3, which then goes and reacts. So that means to actually get the full amount of mass of the entire limestone and not just the CaCO3, you're going to have to undo the percentage, which would be 694.8 divided by the percentage in a decimal, which is that, and that'll give you how much limestone you need, which is 731.4 grams or 731 grams. So it's just really important to make sense of the question here. When I read this question, I thought, okay, well, there's, this limestone is made up of so many different things, and some of it is this. This will go on to eventually make that. And I can see, if I could do a quick sketch, that there's one of these in here, but there's 5 of them there, so there's got to be a 5-to-1 at least ratio of whatever else it can be, right? So then the question's asking me to find out how much limestone I need, but remembering that limestone is not only 95% this, and the rest is whatever it is. So I can use the moles and whatever mass I end up working calculating it is only the CaCO3 part. So if I want to find the whole limestone, I've got to remember that limestone is 95% this. So to get the 100% where it's limestone and the other stuff mixed in, I have to undo the percentage, which is dividing it by the percentage, and that's what we get there. So it's really important just to make sense of the question, sketch out what's going on to yourself, and then start it like that. I never go into these without fully understanding the question, because what's the point of wasting my time trying to dig in my head being like, oh, what do I do next? Huntite is a carbonate mineral with the formula Mg3, blah, 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 whatever, right? So Huntite reacts with dilute hydrochloric acid and it produces a gas and a colorless solution. Construct an equation for this reaction. So start with what you know, right? Like anytime you have a calculation where it's like, construct an equation, just look at the question and say what they've definitely told you. So they've told you that the formula of this thing is Mg3CaCO3, 4, right? They've told you that. Whatever. And also they've told you that it's going to react with hydrochloric acid. So start with writing what the questions told you. The rest can fall into place. Now, it says it makes a colorless solution, bubbles, as well. The bubbles of gas, well, you need to think what your options are. Because it's CO3 carbonate ions, that means you're going to probably be making CO2 and one of the products there, because that's the gas part. Now, as well as that, sorry, this is a solid we're reacting with an aqueous. The rest of it is colorless, so you've got to be making 2 aqueous salts, and also this is a carbonate, so by default you're also going to be making water as well, plus H2O. Now, if we look here, there's Mg3 and there's HCl's here, so that means that we're going to have MgCl2 as one of the salts. That's aqueous, and at least the bare minimum 3 of them, because there's Mg3 there. And if we look at the calcium, we've only got 1, so that's going to be CaCl2, and that's again aqueous. That gives us that sort of, colorless solution. That will give us our gas. That's the liquids. That's fine. To balance this, now we have to look at the rest. So we need how many? So that's what, 6 plus 2, 8 Cls. So I'm going to put an 8 in front of the HCl. That's fine. And then in terms of the CO2s, well, there's 4 CO3s here, so we're probably going to make 4 CO2s. And then if we have 8 HCl, we're probably going to make 8 H2O. So what I do is I always just have a quick look at like the elements that are more interesting first, try and balance them out, and then see if everything else adds up. Because then I know, then you can start thinking about the oxygens and all that other stuff. It's just very easy to start with the big things first. Like 3 mgs are probably going to be their minimum, and then 1 CI minimum. And then to meet that, we need 8 of these. There's probably going to be 8 H2Os, and it all adds up if you check after. That's a way of doing it. So this question's about reactions of transition metal compounds. Ethane 1,2-diamine is a bidentate ligand. Explain why it can act as a bidentate ligand. So anytime you make a coordinate bond, remember, is where you donate an electron pair to something. So anything in the universe with a lone pair of electrons can form a coordinate bond with a metal, right? So that's what makes something a ligand, if they can do that. Now, it's told you in the question that it is bidentate. Bidentate means it can form 2 coordinate bonds. So if it can form 2 coordinate bonds, it must have 2 lone pairs. And if you look at this, the lone pairs are on that end there. Amines have lone pairs on them, unless you have like a quaternary ammonium ion. But for that part, they do. So that's why it can do that, because the nitrogen atoms both have a lone pair of electrons, which can be donated to a metal ion and form 2 coordinate bonds. That's fundamentally what a coordinate bond is. You can't do that if you don't have a lone pair or something to give. Because normally your covalent bond is 1 electron from one from the other, shared pair. But here, both of them are coming from the same species, so they both has to have electrons to give. So the ion Fe3 plus forms a complex ion with 2 ethane 1,2-diamine and 2 chloride ligands. Complex ion A has cis and trans stereoisomers. One of these exists as optical isomers. Determine the empirical formula with the charge of a complex ion A and then draw the 3D structures of these. So we know that we're going to have an Fe, right? Fine. And it's told you that it's doing it with 2 chlorides. So we know we've got 2 Cls there. And it's told 2 Cl minuses, sorry. And we've also got 2 ethane 1,2-diamines. So that means we're going to have, what's that? So it's C, that's what, diamine, so C4. And there's 2 NHs, but then there's also the other NHs as well. So that's going to be what? NH2. Okay, so then that would be C. I'm just working out in my head, so that's that as well, right? So then its empirical formula, we can't simplify that any further, is going to be FeC4N, sorry, H16 N4 Cl2, and the charge is going to be +1, because this is a +3, +1 there. It's asking for empirical formula. It's not asking for any like complex ions or anything like that. That's what it. So now when you have optical isomerism, it's where you've got this non-superimposable mirror images. Like if you put your hands over each other, you can't make them match unless if they're both facing the same way. So when I draw these, what I do is I draw my central metal ion first in either one, and then I put my bonds in place that I'm going to have. So remembering your dashes and your wedges and all that stuff. And then do it lone pair by lone pair. So if we have optical isomerism and it's a bidentate, then it's probably going to be like that and that, right? So then I've just got to draw the actual bit. So I start by drawing the lone pairing bit, which is there. And then the next ethane, sorry, the next ethane 1,2-diamine is going to be there. It's going to be this, NH2. And then I just connect them with the ends. So I know that there's 1, 2, like that. And then I'll do the same here. So I start with my lone pairs, NH2. Just remember to draw the lone pairs on the nitrogen and not the other thing. And then H2N here, like that. And same story. There, there, there. And then for the Cl minuses, well, there's going to be a lone pair here. And then it's also got a Cl here as well with the lone pairs. So now that that's done, you've got that. It's just a mirror image. So again, NH2, H2N, like that. And then again, H2N, NH2, there, Cl, Cl. So that's how you draw complex ions. You do it lone pair by lone pair, and it gets very easy. Now that's your optical isomers. Then you think about your cis-trans isomerism. So cis-trans isomerism is where you've got, it's like EZ, but on the opposite sides or same sides, right? So in the context of transition metals, if you've got an octahedral complex, opposite sides are going to be a trans thing. So we need the trans isomers. These are your cis isomers because they're on the same sides-ish technically, we're speaking, so there and there. So there's trans isomers is where you basically have something on the opposites. So it's usually the top and bottom are opposites. So I can put the Cls there. So if I do this again, it's the Fe, going to draw my like dash lines and wedges and stuff, like so. Whoops, that is a terrible wedge. And then I know, well, these are going to be on opposite sides, so Cl, Cl. And then I've got my NH2s because my lone pairs, I'm doing it lone pair by lone pair because that's a lot easier. H2N, H2N. If you're not drawing it lone pair by lone pair, what are you doing? Like this? I'd probably do it a bit better than this. Actually, a better way of doing it is you could do it. So lone pair, H2 like this. It's a bit hideous, but it's still doable. And H2, and H2, and H2. There. That's a lot nicer and a lot easier to see. But there you go. That's what they are on opposite sides. So now it says aqueous sodium hydroxide is added to an aqueous solution of iron 2 sulfate. A pale green precipitate forms, which then turns brown when left to air. So write an equation for the formation of the brown pale green precipitate. So ionic equation, if we're adding that to sodium hydroxide, NaOH, the sodium is just the source of the hydroxide ions. So what you're essentially doing is you're reacting Fe2 plus aqueous, and you're adding OH minuses. And they've told you it makes a pale green precipitate, so your option is probably FeOH2, solid. And you just balance it, so it's a 2 there, done. It says, use the information to explain below why the green precipitate turns brown when left to stand in air and construct an equation for this when it occurs. So a lot of people will jump in and be like, this must be oxidized, this must be reduced, or something like that. Just pause for a minute and forget all of that and look at what the question's telling you first. Maybe it is the case, but sometimes there are scenarios where they tell you a reaction happens and it's not actually oxidation reduction, it's the other way around or something like that. So I always say, look at the question, what reaction are they telling you is happening first? If they haven't told you that and they're telling you to decide what's happening, then you start doing that. So the question has told you that what? We have Fe2 plus aqueuses, right? But then it's to explain why the pale green precipitate turns brown when it's left to stand in air. So we're definitely starting with this Fe solid where it's got the 2 plus in it. The 2 plus ion. FeOH2, sorry. Okay? And it's told you that it turns brown. So you need to be able to recognize what that actual brown precipitate is. So the brown precipitate is FeOH3, solid. That's what it is. So now we know that this reaction, the first one, has to go that way, which fits the bill because that's getting oxidized, and you're looking at that and be like, oh, this is right, but like they told you in the question that this is the reaction that's happening. You need to explain why it happens, and that's where you go and start realizing the next parts. So what I mean by that is that this electrode is now going to be FeOH2 solid plus OH minus aqueous goes to FeOH3 solid plus E minus, right? That's oxidized, and because you've got an electron on this side, and that's changing from an Fe2 plus to 3 plus. That makes sense. So that is oxidized, and that's what we see. That's more negative. That's what we're familiar with, right? And then this is reduced, so the other one has to be reduced. So that means we're going to have what? So O2 gas plus 2H2O liquid plus 4E minus gives you 4OH minus aqueous. Remember that these are still equilibrium things, right? So it still happens, but that's happening that way. Now what we do is like we always do, we times that by 4 and we'll put them together. So if I just combine those now, we get 4FeOH2 solid plus 4OH minus aqueous plus 4, sorry, no, not 4, O2 gas plus 2H2O liquid. Well, you don't need the 4A minuses because they cancel out now. It would give us what? FeOH3 solid, well, 4 of them, sorry, plus 4OH minus. So aqueous. So that cancels out, and we are left with 4FeOH2 solid plus O2 gas plus 2H2O liquid, and technically speaking, this is an equilibrium as well. Gives you 4FeOH3 solid, right? So that's us constructing the equation. But then it says use the information to explain why this happens. So again, obviously we would jump straight to saying oxidize and reduce, but the question might have said why does this not happen and show you the other way around instead. So that's what I mean is when you're doing these questions, look at the questions telling you first, and then you know. So then you can start to say, well, that's oxidized because you'd write somewhere that that's oxidized because your E cells more negative, and then because E cells more positive, and then well, why does it happen? Any ideas? Why does this reaction happen? Because if we work out the E cell, that's E reduced minus E oxidized, that's going to be what? 0.40 minus 0.56, which is 0.9 plus 0.96 volts. That's greater than 0, therefore it's feasible, so that's why it would happen as well. It doesn't, if it's not feasible, it doesn't happen. Like it doesn't mean that it's not going to happen, sorry. It just means you got to put a lot of energy in, because remember, feasibility means that if you start a reaction, it will continue to completion without having to add extra energy into the system. So it can still happen if you kept pumping it with energy, but this will happen on its own because it will happen, to completion if you start it. So it's feasible. So that's what I would do in these questions, is every time you have an electrode potential question like this, look at the question and say, what have they told us what we're starting and finishing with? Because it might not follow your oxidized and reduced. Because the question could have just said the opposite and been like, why doesn't this happen? Then in the other one, this would be reduced, that would be oxidized instead, even despite the numbers being that way, because you can force them to go the opposite way. So that's what I mean by that. But there you go, that's how I handle that. This question's about copper and copper compounds. Hydrochloric acid is added to an aqueous complex of CuH2O6, and it gets a yellow-green complex forming B. And then what else happens? You heat it with concentrated sulfuric acid, reaction takes place, we get a pale blue solution C and this much gas at room temperature, and the mass of the gas is that. And then the excess of CuO is heated with dilute nitric acid, the resulting mixture is filtered, and you get a filtrate that is a blue solution E. Aqueous potassium iodide is added to this, and then a white precipitate aqueous potassium iodide is added to E, and then you get a white precipitate F and a brown solution G formed. Determine the formula and construct equations and changes of any oxidation numbers as well that are relevant. So this whole thing is an absolute, hellhole of a, mess going on. However, if you just take it step by step, then it's very easy. It's very tempting to jump back and forth and be like, oh my God, what do I do? Don't do that. Look at the facts of the question and see what happens and do it step by step. So the very first experiment, they've told us that they've reacted objectively from this question. I can conclude. So we should always do that is look at the question and say, what can they you definitely say is happening. They've told you that this thing, so you're reacting CuH2O6 with HCl, however much it might be, is definitely making something that is yellow-green. If that's happening, our options are either we're getting CuCl2, which is a salt, which is not happening, or ligand substitution happens. This is one of the examples where ligand substitution happens, where the blue goes yellow-green because you've got these Cl minuses, but Cl minus is gigantic compared to H2 and Na3, so you can only fit 4 around. So this is one of those, one example you should know about, which is where you get CuCl4 2 minus aqueous plus 6H2O liquid. And that's a ligand substitution reaction where it goes yellow-green. And that's what B is. There you go. We figured out what B is straight away. And then obviously balancing it out, we would just have a 4 there. Right? That's that one done. So now we've sorted out what B is. The next one says, a piece of copper metal is heated with concentrated sulfuric acid, and a reaction takes place where you get a pale blue solution C and then this much gas D measured at this temperature, and the mass of the gas is that. So, again, look at the question. The question has objectively told us that we're reacting a solid copper, a piece of copper metal, with concentrated sulfuric acid. The question's told you, so you're making a pale blue solution, so that means you've got Cu2 plus ions here. So that means you're going to have CuSO4, right? Aqueous. So that's fine. But we need to now look at what else we're making. It's not going to be H2 gas because we need to factor in all of the oxidation statey bits. This has gone from 0 to +2, which means it's lost 2 electrons. Something else will have had to take the 2 electrons. Now, generally speaking, these two always, oxygen and hydrogen always keep their oxidation states the same. So the only thing here that must have taken those electrons away is this. So again, we've lost 2 electrons. That's probably nabbed 2 electrons. So if you look at the oxidation state here, that's -8 plus 2. So the oxidation state is +6 here, right? If it's nabbed 2 electrons, it's made something where sulfur has an oxidation state of -4 because it's gained those +4 because it's gained them electrons. So then we just muck about the elements. The other thing's got to be SO2 gas because that's a -4 oxidation state. And I'll give you the overall thing. And then what's left is we have to deal with them hydrogens, and we're making H2O like that. And if we balance that out, we'll have, well, let's see. So there's 2 S's there. So there's 2 there. There's 2 there. Liquid. Done. I think that is it. Yeah, there you go. That's how I hack it because you need to remember, think about oxidation reduction and all that kind of stuff. It's all to do with electron transfer and stuff. It's not just making like a salt plus hydrogen. This has lost 2 electrons. Somebody needs to take them 2 electrons. The only thing that will be is this S here. So that's that. And we can figure out gas D like that. But as well as that, they've told us that this is happening at room temperature as well. So the other alternative is you could do the moles equals the mass of the gas over over 24,000 or 24 decimeters cubed, which gives us the moles of the gas that we've made. The moles of the gas that we must have made is 1.875 times 10 to the -3, and they've told you that the mass of this gas is 0.12. So if we did 0.12 divided by its moles, 1.875 times 10 to the -3, we would get the MR of the gas. So you do this to confirm it as well. And if we do that, we get an MR of 64, which actually adds up to SO4 as well. So that has to be your gas. So that's what you could do as well, the alternative way. So I did it like that, but you could do the other way around when you work on the moles of the gas. You'd see that this gas is 64. So H2 would not give you 64. The only option that could would be SO2 as well. So we know what C is now. We know what D is. Now if we look at the third experiment, an excess of copper 2 oxide is heated with dilute nitric acid. So again, good start is to just, think about the reaction that's going on here. So here we have definitely been told that CuO, solid, is going to be reacting with, where's it gone? Dilute nitric acid. So we know that it's reacting with HNO3. Don't know how many, don't know what's going on, just thinking about it just like that. The resulting mixture is filtered, and then we get a blue solution. So if we're making a blue solution, the oxidation state of copper must be Cu2+. So that means we're going to be making CuNO3, 2+, and then whatever's left over, well, oxide plus nitric acid, a metal oxide plus water gives you a salt plus water. Sorry, metal oxide plus acid gives you a salt plus water. There. And now we need to balance that out. So we've got 2 NO3s here, so we need a 2 there, and then that's the 1 oxygen for the 2 hydrogens. We're done. There. So that's that. The resulting mixture, it's a blue solution E. So we now figured out what E is. E is that. And then what else? So it says here aqueous potassium iodide is added to E, and then you get a white precipitate and a brown solution. So we're adding this solution E. So now we're, again, objectively from this question, we know that we have CuNO3 2 plus Ki, right? Is that the aqueous, right? And they've told us we're making some mysterious, where is it? Where's it gone? A blue solution has been reacted, and we get a white precipitate and a brown solution. So the brown solution has to be from that iodine, so it has to be I2, whatever, right? If we have a loop, we need to think about what's happening here then. So if we're making a white precipitate, then it means we're making something that is solid. Now, if we just have our CuNO3 and stuff, it'll just dissociate again because it'll just keep staying as that sort of blue solution. So we need to look at the oxidation states again to compare side by side because that's the only thing that's different in these sides. So this oxidation state of iodide is -1, but that's gone to 0. So where something has lost electrons and has become oxidized, something else has to be reduced. You can't have one or the other. It has to be reduction happens as well as oxidation to something else. So if that's the case, then if each one of these loses 1 electron, then something else has to nab them. So it's probably the copper that's gained it. That NO3 is probably going to stay as NO3. So if that happens, then the options are we go from Cu2 plus, because that's what it is now, to Cu nothing, would have to make elemental copper, but that wouldn't make sense because it would tell us that there would be like a copper, metal, like a brownie colored one. So it's not that. It has to be something else that isn't just copper metal. So the only other option is that we can make it gain 1 electron. So it's probably become an oxidation state of 1, Cu, right? Now, this is going to react with this. Potassium is probably going to nab the NO3s as well, just to make it like, what's the word? To continue keeping that part the aqueous solution. So KNO3, because remember that these stay the same oxidation state. That stays the same oxidation state as well. So it's probably that, and we've got 2 lots of that. Now, I'll balance it later. Now, sorry, if that's got like oxidation state of now 1, probably going to take one of the I's as well. So it's going to become CuI, solid. And that's what happens. So if we now try to balance this out, we have what, an I here. We've got 2 I's there. Let's try putting a 2 here, and then we could put a 2 there because there's 2 coppers, and then that means how many? That's 4 I's. So 4 there, and then that gives you a 2 there. Does that work out? No, sorry, not a 2, a 4 because there's 3 N's there. So if you do it like that, there you go. That's how you do it. And that's how I sort of figure it out, because as well as that, you should know that in one example, you can react Cu2 plus and reduce it down to Cu, which is exactly what's happening here. And that's CuI is the white precipitate as well, and you can get disproportionation of Cu plus ions as well and so forth. But that's the detail this question is. So that's how you determine what all of them are there like that. So you can do a bit of problem solving using the question and what they're telling you. I hope that helps. Thank you very much. Please like, share, and subscribe. You know the drill. Bye bye.